second. Looks like we're getting close. This is now my second live mini course on the coronal holes and sources of slow solar wind. And okay, looks like we're about to go live. So I wanted to say hi to all of you. I hope you guys can see me. Please let me know if you can see me and if you can hear me. And I will be very, very, very excited. Started streaming less than a minute ago, but I don't see myself yet on the live. Oh, here we go. Okay. Good. Can you guys see me? Everybody hear me? Everybody see me? I see myself live. I may have to turn down the volume. I've got my computer on and I'm looking at it and I hear the headphones. I hear the cans. I can hear myself echoing a little. So I may have to turn it down. Hey, Jerry, good to see you. Yes, I do have my mason jar, just in case you wanted to see it. Yes. Of course, where would I be without it? Hopefully you're drinking your coffee out of your mason jar. Apparently I'm making this fashionable. Who knew? We break so many things in our house all the time. The glasses are like one of the things that get broken because I have a 10-year-old. So we just started drinking out of, you know, jelly jars and mason jars because we could recycle them. They're really easy and, you know, we don't have to get upset when we break one. So that's really the origin of the mason jars. But yes. So if this is becoming fashionable in your household, I'm grateful, I'm honored that you would do that. So here's to you, Jerry, and thank you for being on. He's one of my VIPs for Patreon, so much appreciated. Okay, let me turn this down because I can hear myself too much, and it's driving me nuts. It sounds like my audio is doing all right. I am hoping that it will not crash. If it does, I do have my phone with me, as always, so those of you who are my Patreon VIPs, you have access to me, and please text, call, do whatever you need to do to make sure that I, you know, don't have 17 minutes of audio-less course. Although I am watching now, so it's a lot easier. So hi, Jim. Hi, Scott. Hi, Paul. Mike, I'm glad you're on too. He's another one of our VIPs. Love Ball, thank you. Jonathan, thank you. Vegan Crane, thank you. Lee, appreciate all you guys coming on. I am very grateful that you guys are joining me for the second of our courses on coronal holes in the solar wind. And all of this is only made possible by everybody on Patreon. First, I of course have to thank my VIP steering committee. These are all the people that have helped steer the ship over, and some of them over the course of the entire time I've been on Patreon. I can't do any of this without you guys, and we have some more really cool stuff coming up, including that talk I'm going to give to the FAA. Some interesting things that are going on with NASA and APL regarding the Artemis mission. I don't know if I'm going to have time to be able to deal with that this semester, but it's maybe a neat opportunity if I can squeeze it in. I just don't know how I can. And then, of course, the second of the set of mini course or major courses I'm now teaching at Millersville University. That maiden voyage of that second course is this semester. So it's really a busy time. But you know, all of you guys have helped tell me where I need to be, you know, putting my efforts, what part of the community really needs the most help when it comes to space weather and who are really affected by it. And your voices mean so much to me. So thank you so very much. And then also my mini course patrons, I wouldn't be able to do these live mini courses on YouTube if it weren't for you. You guys help tell me what the course material should be and what order I should do it in. As a matter of fact, we're coming now down to the close of the space weather phenomena in terms of just the stuff that comes from our star. Next, after the end of this one, we will, I mean, we could do anything. We could go into the heliosphere and talk about the solar cycle a little bit. We could go, someone had asked me about the history of space weather. We could talk about that. We could also go specifically into effects at Earth in a specific arena, which is some of the stuff I'm teaching in that new course, SWN 572. Or we could, you know, we could do a left turn and I could do a deep dive into how to read my space weather forecasts on a weekly basis. I know that's been a very popular request for quite some time. So all my mini course patrons, you all get to help decide what that material will be for our next course. And I'm really looking forward to it. So thank you so much. Again, it means the world to me. And I'm so glad to see so many of you here live with us right now. Mein Kampf, good to see you too. Lee Cunningham, thank you. Comedius, Dave, all of you guys, good to see you. Tamitha, does the moon have any magnetic field to deflect the solar winds? No, actually, and that's a big deal for Artemis. The moon is really just the crustal, like a crustal portion of Earth, we think. We think there was a big, meteor or some type of asteroid that hit Earth, and it literally ripped during the early formation, reasonably early formation of Earth. It ripped part of that crust off. So the moon has no iron core. And because of that, it has no chance of even having anything but remnant magnetic fields that are very, very weak. So no, it doesn't deflect any of that. Now it does go in and out of the Earth's magnetic field. It crosses through the magnetotail, as we call that, quite a few times. Well, obviously once every time it, orbits the Earth. But it sits a lot of times out in the interplanetary, just in the solar wind. So it's going to be a very interesting time for people who, for astronauts who want to try to colonize the moon, because they are going to get a big dose of radiation from both cosmic rays and from solar energetic particles. So that's a big issue. They'll have less of an issue with solar storms. When a big CME comes by, that's not going to be nearly as much of a problem for them unless they're inside Earth's shield. But radiation, they're not shielded from at all. So that's going to be their big monster. That's probably going to be the hardest thing for them to deal with. So, good question. Okay. Oh, thank you, Mac. I appreciate that. Okay. And greetings from Germany. Thank you, Comedius. I appreciate you tuning in from Germany. I know it's late there. I hope Deepak is on, because he's tuning in from Jakarta. So, my goodness, it's like 1 a.m. there. So, if Deepak, if you're on, I'm much appreciated. Okay, guys. So let's get started, huh? You probably are so sick of this slide, I can't even tell you. But I always start off every class with this slide just to remind everybody that there are 4 basic types of solar phenomena that affect Earth. Okay? And we've gone over all of these, except we're now going over the coronal hole part, right? We've gone over solar flares, we've gone over solar storms. They're not the same thing, although a lot of people think they are. Both of these things actually drive solar radiation storms, and you can see the blizzard here. I'm not going to play the movie, but there's a blizzard that we get in our coronagraphs that blind us. I mean, this is actually what the astronauts see too. They get all these little fireworks in their eyes because of the energetic particles that hit. And then outside of that, we also have fast solar wind from coronal holes. Now, coronal holes can also drive radiation storms behind me, but not very often. At least not at Earth. It's not very easy. It depends upon how fast the solar wind is. They can drive shock waves, and if they drive shock waves, that fast solar wind, then yes, they actually can drive radiation storms, but it's not nearly as common. 4:09 a.m. in Australia. Oh my goodness. Thank you, Awesomeness. I appreciate you being up so early for this show to catch it live. So definitely post questions, guys, if you have them, and I will do my best to answer. And again, Warren from South Africa, thank you so very much. Okay, so these are the 4 phenomena. If you guys have not seen my other mini courses that on these other phenomena, please check them out. They're very long. They're like 3 hours, but they're a lot of discussion because we spend a lot of time just discussing, and I break for questions and things like that. And so what I'm going to do now is I'm going to give you kind of a refresher. Remember, this is the second course on solar wind, the sources of the solar wind and what coronal holes are. So I'm going to give you kind of just a refresher of what we talked about last month. These are coronal holes. I did show this plot last month. Here are several different pictures of the sun, and I believe they're all but one of them is actually this 171 image is not the same time. All the other ones, the red sun, the bronze sun, and the pink sun, are all at the same time. But what we're looking at in these images, this is the AIA instrument on SDO, the Solar Dynamics Observer that is sitting staring at the sun all the time, looking at the sun in extreme ultraviolet, which you can only see from space. This is why you can't see this stuff from the ground. If you look at the sun in different wavelengths, you will see different things. So what looks like a coronal hole in the pink sun, for example, all those dark, really dark patches, right? Those dark patches, those are coronal holes. Right there, you see one there, you see one in the south over here, right? You see a couple smaller holes up in the north. These are not real holes. They're just not emitting light in that particular wavelength, okay? So if I switch to a different wavelength, here's one where you can actually still see the coronal holes, but they're not quite as dark, right? Because it's actually beginning to emit light in that wavelength. And if I switch over to 304 angstroms, this orange sun, look, do you see any holes at all? Not really, right? Because there aren't any holes. It's just that those areas are emitting light in this wavelength, and in this wavelength they're not. So it's cold, and so it looks like a hole, but it's just dark. It's just not emitting light. Don't worry. When you see these huge holes on the sun, they're not holes. We just call them holes because that's where the fast wind comes from. That's just scientists' way of talking about it. But don't take us literally, because that's not really what we mean. By the way, this particular, someone asked me a while back, this particular image has magnetic field lines overlaid. This is not, so these lines that you see coming out of this pink image are not real. They're a model that's overlaid on top. What they're showing is that you've got these big magnetic loops that enclose all the bright regions. You see how it's like what we call closed. Kind of looks a little bit like a slinky, right? We've talked about this in the past, where it looks a bit like, you know, magnetic field looks a little bit like this. And you see these closed loops all around the sun. As a matter of fact, this is a slinky, if I can put it in the right place. This is a kind of a slinky that looks like this. Did I tilt it and move over here? Okay, so this is it's not supposed to disappear on my green screen, but I painted this thing white so it wouldn't disappear. But I see it disappearing. So if you can imagine this big slinky coming out this way and back in a little bit, that's kind of what you're looking at when you're looking at these fields, okay? But notice if you can look in the coronal hole region, all you see are straight lines that come out, right? Those are called open magnetic field lines. That's where fast solar wind escapes, okay? Slow solar wind comes, we believe, I mean, Parker Solar Probe has kind of proven us wrong to some degree, but we believe slow solar wind comes from the regions that here that are kind of closed. The fast solar wind we do know comes from these coronal holes because that's open and the solar wind is more easily, or escapes more easily. Don't worry, you know, the sun isn't gonna, it's just losing a little bit of its atmosphere. It's not gonna explode or anything. But that's what we talked about last time, and with this much dynamic, you know, structure on the sun, you're going to expect to see solar wind that's going to be very dynamic and structured. Think about the sun as something that can, you know, all of its magnetic field and all of its structure actually stretches out into the interplanetary medium, right? So you just kind of think of what that would look like if it expanded, and you can already tell just by looking at this picture that, wow, that's going to be a pretty dynamic and pretty different, you know, a very variable solar wind coming off of this, okay? Hopefully that makes sense to everybody. Oh, the Netherlands, hi. Let's see, will the overabundant satellites have any effect of shielding the Earth, or will the sun-facing satellites be destroyed during a solar storm? No, we have satellites all the time that look at solar storms. We know how to design these things so that kind of thing doesn't happen. Although every now and again we get bad things happening, and I'll talk about that. I'll talk about that near the end of this course. We'll talk about how believe it or not, satellite operators at geosynchronous, that worry about geosynchronous orbits and their satellites there, they worry about the health of and safety of their satellites with fast solar wind streams, even more oftentimes than solar storms, because during a particular phase of the solar cycle, they just get hit over and over and over again with fast solar wind. So we'll talk about that. Anyway, just again review that, and I already kind of mentioned this, that the sun creates both slow and fast solar wind. You can see here, this is time going across down there, and it's going up is speed of the solar wind. And this was from Ulysses data, and we'll show some more Ulysses data because it was a fascinating mission. This was the only mission that we've had where we actually had a spacecraft go over the poles of the sun, which taught us so much about the solar wind we couldn't even believe it. But as it began to do that, it saw when it was sitting in the ecliptic plane down low where we are, where Earth is, it saw a lot of slow solar wind, and then as it started going to higher and higher latitudes, it started seeing fast wind streams. So it goes fast, slow, fast, slow, fast, slow. And then as it continued to go into high latitudes, all it saw was the fast solar wind. So once it got to a certain latitude, high latitude, near the sun's poles, that's where it really saw just straight fast solar wind. It saw no more slow solar wind. So we'll talk about how not just latitude makes a difference when it comes to the speed of the solar wind and the structure of the solar wind, but also what time in the solar cycle. Okay? Because, yuck, it's a mess. It's an absolute mess. There's so much stuff. We're learning that there's spicules and this magnetic carpet that we see with just little tiny microprocesses happening all the time. And I think we drew this, yeah, back in 2008, Wiedemeyer drew this. This was before Parker Solar Probe. It's even messier than this. And even the solar wind that's blowing out of the sun, right near the sun, is very messy. It looks just like this. It's just, it got switchbacks and folding things and all sorts of little, oh, it's like bubbles of stuff everywhere. So we're learning a lot about it because of Parker Solar Probe. It's going to take us probably more than a decade to sort it all out, believe it or not. All right, so on top of that, we do have a potential field source surface model, the PFSS. That was what you saw in that diagram that I was showing you, the magnetic field lines and the slinky, right? That's the model we're looking at, okay? And this is a kind of a messy way of showing it. I hope it's clear enough on the screen for you. But it's overlaid on top of this this corona, like it's a coronagraph. You can see some streamers blowing out in this coronagraph. But the field, this potential source field model is color-coded green for open field lines going out of the north, blue for open field lines going out of the south. I don't know why they chose blue, because the coronagraph itself is kind of bluish, so it kind of just fades in. And then you've got closed field lines that are labeled both orange and red, depending upon the height, I think, in the altitude of or height in the solar atmosphere. And if you kind of look at the way these field lines are, you can see they blow out open field or open solar wind here and here. And then you've got these slow solar wind, more dense structures. See the streamers that go out? Okay, those are more dense. That's why they're kind of light colored. They're kind of thicker to see in these coronagraphs. And so this is where the closed field structures are. Okay, so the slow solar wind kind of blows out where these streamers are, and the fast solar wind is blowing out where in the polar regions where the open field lines are. This field model helps us see very much where those coronal holes are and gets us to understand whether or not we're looking at the magnetic field the right way. Because if the open field doesn't align with where those coronal holes are, boy, we're in trouble. But it tells us something's wrong with the model. But it's been very helpful to help us learn about what really drives fast solar wind and how it really works. So, like for instance, here this isn't exactly the right connection for the image, but it's close. So you've got some streamers here. Let me get my hand in the right place. You've got some streamers here, right? You've got a big helmet streamer down here as well. If I can get my hand in the right place again, come on back. Here we are. Here's a helmet streamer. I talked about all of this stuff last time. We can have sector boundaries where you have the magnetic field blowing out, pointing outward in one, and on top of that heliospheric sector boundary, and when pointing inward beneath it. So that actually starts forming the current sheet, and that's to do with the neutral line on the sun. Probably should have shown a slightly different image for that. But here's a better picture of the neutral line, which of course changes depending upon if you're dealing with solar minimum or solar maximum. Again, these are all reviews, so if you're trying to remember what these slides are, please go back to the prior mini course. That's where I go over them in detail. This is just to kind of get your mind, kind of warming up for this next set of stuff. So here was solar minimum. This is the Mount Wilson Solar Observatory. They're looking at the magnetic field of the sun at the surface of the sun. They're looking at outward field and inward field. The white, I think, is inward, and the black, I think, is outward pointing. And so they can draw kind of a fuzzy little neutral line, magnetic neutral line. It's kind of like the equator, but it's the magnetic equator. And you can see it's almost flat near solar minimum, okay? And you can see there are very few sunspots at this time. And by the way, this is what we call a Carrington rotation. It's basically one full rotation of the sun, and we basically stretch out, just like we do with Earth maps. We stretch out, the globe to make a flat map. Exactly the same thing with the sun, but it's done in time. Because we have to wait for the sun to rotate over us. So the beginning of the map is 20 days, 27 days sooner than the end of the map, sadly. So it's not a snapshot in time. It's, unfortunately, it progresses through time, but it's the best we can do right now. We do a little bit better with stereo, but not much, especially with stereo B being gone, sadly. But at any rate, so you can see the neutral line being reasonably flat during solar minimum, very few sunspots. Those are the little black and white, what groupings, dipole groupings here, right? All that you see spattered up. I think there's like 5 of them. And then down here, you're seeing on this bottom plot, you're seeing the solar wind speed. So blue is really cold, dark blue is really cold and slow, sorry. At like 200, does it say 250 kilometers a second, and then red is about 750 kilometers a second, so red is fast, blue is very slow, and you can see right where that neutral line is, that's where we're seeing where all that slow solar wind is, and then near the poles during solar minimum is where you see where the fast wind is, the red stuff, okay? When we switch to solar maximum, however, or near solar maximum, oh my goodness, things change dramatically. As you can tell, we've actually switched polarities. Now we have black on top and white on the bottom, compared to what's behind me, right, where I was actually looking at white on the top and black on the bottom. So the sun's polar field actually flipped in this, comparatively speaking. But you can see near solar maximum, boy, we sure have a lot of neutral line movement, right? It's really up and down at high, it's no longer flat, it's moved to high latitudes. It goes from high latitude in the north to high latitude in the south and back and forth. I just realized I forgot to mention that this is a plot of time versus latitude. The equator is in the middle. I'm trying to go through these too fast. The equator is in the middle, and latitude going up to, I think, is up to 90 degrees in the north, and then latitude going down to 90 degrees in the south. Okay, so that's what each one of these plots are. My apologies. As you can see, however, the sunspots, they're all over the place. And then, of course, the solar wind, right? Now it's kind of smeared out, but you actually are seeing, in this case, you're seeing, you're not seeing a lot of coronal holes necessarily, not super fast wind. You still have fast wind at the poles, but you are seeing faster wind, kind of see where the green is, for example, kind of protruding clear down into the equatorial regions. That's, for instance, due to a coronal hole. Okay, it's not just this smooth band of slow solar wind at the equator anymore, like you see for solar minimum. Now, if you take that and you stretch it out, remember all this stuff blows out away from the sun. Now you're going to fill a heliosphere. You're going to fill the entire solar system with this solar wind that has kind of this signature as it leaves the sun, this signature or something like this when it's near solar maximum. And so you can imagine if your Earth kind of flying through this stuff, you're going to end up getting all sorts of like fast wind, slow wind. You're going to get undulations. You're going to get magnetic field going outward and then inward. It's going to change as you go past the current sheet. All of that stuff. And sure enough, let me do, okay. I think I might have, do I have arrows? Yeah. How many arrows? Just 2 arrows? 3 arrows. Okay. So, you know what, let me back up. I'll just talk about this first. So, I had to remember how I did the plot. This is Carrington rotations again. This is from 1983 on down to, there's 1988. And then the next one goes from 1989 to 1994, okay? So it's contiguous all the way down. You kind of read it like you'd read columns in a newspaper. And you can see in 1983, that magnetic field being black on top and white on bottom, it was reasonably smooth. It gets even smoother as we get to 1986 and 1987. That's because this was what solar minimum was for this particular solar cycle. This was cycle 22, I believe. And then as we started moving through that down, got past 1998 to 1989, look how lava lampy the sun got. I mean, you basically go from something that kind of has a lot of wiggles in it, in that magnetic neutral line, to islands, right? Bubbles, all right? Now imagine what the solar wind must look like as you go through this, okay? This is because as you get to solar maximum, we have what we call a multipolar sun. The dipole field is gone. Gone is the pretty days of ordered solar wind and ordered magnetic field on the sun. It's just a mess of different bubbles. It's that magnetic carpet that we talked about all over again. And then as things begin to calm down, as we get out of the solar maximum and into the declining phase, things begin to smooth down again. And there is a method to the madness. When we have, I'll try to stand way out of the way. When we have the declining, or the ascending phase of the solar cycle as well as the declining phase, we have a nice dipole field of the sun with the streamers, but it's tilted. And so you get, that's why you get this as the sun rotates, it kind of makes this like tilted kind of thing like this. I always do this with everybody. I had people wearing sombreros in my Millersville class because I kept saying the ballerina skirt was like a big sombrero. But you get that with the neutral line, whereas if you're wearing a tilted hat and you rotate, then sometimes you're going to hit part of that hat, and other times you're going to go, you're going to go above the brim or below the brim. It depends. And so you're going to either hit fast wind or slow solar wind, depending upon where you are. And that's really why you see that such a tilted heliospheric neutral line, that magnetic neutral line, is because you're seeing a lot of this tilt, and you're seeing that neutral line kind of wiggle as the sun rotates around. Now, as you go to solar minimum, where everything is very flat, that dipole field is no longer tilted. It's straight, because the dipole field at that point is very well formed. It's not competing with any of the other field components. It's dominating, and so that's what you see, is this really nice dipolar field, and that's what gives you this beautiful thing. This is where we are right now, for instance, in the sun, in our solar cycle. We have a very well-formed dipole field, and we are kind of waiting for the tilt to come back, because that's what's going to happen, is the tilt will come back. And then once you get past the tilt and your dipole field dies out completely, you've got what we call a multipolar sun, if I can put my hand in the right place. And I hate to say it, it looks like a coronavirus. But it kind of does. It's just stuff sticking out all over it. We say the sun has coronavirus when it's at solar maximum. That's kind of weird, isn't it? Because it's a corona. I don't know. I don't make this up. This is real life. So anyway, this is what the magnetic field neutral line ends up looking like when we're at solar maximum, is that it ends up looking very much like a lava lamp with all these little islands, with all these little things sticking off the edge of it. So it doesn't mean the corona's sick, it just means we're at solar maximum and the dipole field has gone away, and all the other smaller components to the sun's magnetic field get exposed. I think in the past I've talked about it like, because I have a 10-year-old, I talk about it as like a bathtub being filled with water. And as long as the water is up to the top and there's all these submerged toys underneath, you can't see the toys underneath this murky, soapy water. Right? It's only after you drain out that water do the toys begin to emerge. And that's exactly what happens with the sun's magnetic field, is that as the dipole field begins to shrink and get smaller and smaller, all the other toys begin to emerge. All of the multipolar components of the sun's magnetic field begin to show up. Right? But we don't know that. If the dipole field is strong, it's like the bathtub is filled and all the other components are hidden under the water. So hopefully that makes sense to you guys. So, on top of that, let's see, awesome explanation. Oh, good. Okay. How long till we see significant solar activity? Oh, yeah. I'm hoping within 6 months. I mean, we have been starting to see it already. We just haven't gotten the flares yet. We're seeing filament channels fill in, which is nice. We had a first big filament eruption just this past week, and that's definitely a new thing. So we're very excited about that. We just need those sunspots to get more flare active, and then we'll really be happy. But we're hoping within the next 6 months. Okay, so I talk about the sun's magnetic field, right? And we talk about that neutral line. And again, if you want a really in-depth class, then go see my part 1 of this course. I'm still doing the review, but we're almost done. And then I'll play a neat movie that kind of puts it all together for you. But on top of that, we have something called the Parker spiral. And if you guys recall, it basically has to do with the fact that the sun, let's see if I can stand on the right side here. the sun is, as it rotates, if you're looking down at the sun from the North Pole, let's say, okay, the sun is going to be rotating like this, okay? And as it does that, it's shooting out solar wind all the time, okay? But if you've ever seen like one of those garden sprinklers that spin as they spray water, do you ever notice when those spinners, how they seem to like let these spiral streams of water? It's like the water's actually doing a spiral. Well, you know that a stream of water can't spiral, it doesn't curve. But it's an illusion, in a sense, in the way that the sprinkler's spitting out little bits and pieces of water, little parcels of water. But as it rotates, it spits out another piece, but that piece is not aimed at the same direction it was just a moment ago, because the sprinkler head has moved, has rotated. So it spits out something this way, and then it rotates and spits out something this way, and rotates and spits out something this way. But by the time it does that, the first piece that it spit out is shot a lot further away from the sprinkler head than the piece it's just now shooting out this direction. And if you were to connect all of them with a spider web or a line going through them, you would see that it would make a spiral kind of thing, which is what we're really talking about here. And like I said, I talked about this in great detail during our last class, so I won't go through it again. But this is what we're talking about, how it was illustrated, was that every single one of these little arrowheads is trying to show a piece of a plasma, let's say a parcel of solar wind, right? Or if it were a sprinkler head, a parcel of water that's being shot out by the sun. But the sun at the same time is rotating. So the stuff that it shot out, you know, that came out along this arrow, for example, which we're saying is 7 days ago, that stuff is really far away from the sun now, okay? But that was when the sun was rotating, shot out a piece of you know, the same source region that's now clear over here. Oops, let me get over here. This source region, whoops, I have to go higher. Where am I? There I am. Look at me, the drunken sailor, right? My green screen makes a delay, so I always overshoot. Okay, so this solar source region 7 days ago was over here. Okay, it was over here. And it was shooting a piece of plasma out along that line that's behind me, which I'll get out of the way of in just a second. And then as it rotates, it rotated to here, and it shot out something else. And then it rotated again, and it shot out something else. And it rotated again, and it shot out something else. So as I get out of the way, you can see that. Okay, so each one of those arrows are showing how it shot out plasma as it was rotating. Okay, so we're looking at a single source region on the sun. We're not looking at the whole sun, because the whole sun is doing this all the time. But we're just taking apart just a tiny bit. And the reason why we're doing that is because of the magnetic field of the sun. It's tied to the source region. So the magnetic field threads through all of these plasma parcels that the source region shoots out. Okay, it doesn't matter it left 7 days ago, the magnetic field still has to thread through it, just like a spider web. It threads all of these, kind of like identifies them as coming from that single source region. And because of that, it makes this spiral, okay? And that ends up being what we call the Parker spiral, okay? And you can see here, no, here, let's do this one. Here is looking down at the sun, again from the North Pole. Now the sun is now just this tiny little dot, right? And you're seeing straight arrows in that blue circular region, showing you the directions that the sun is blowing out solar wind all the time. It's always coming out straight, always being blown out radially, okay? But because the magnetic field has to thread through all of this, each magnetic field line is threading through a unique solar source region, only one solar source region. And it threads everything and identifies everything coming from that source region. It ends up making a spiral. It looks like a pinwheel, believe it or not. So that's one cool thing, is that you get this beautiful pinwheel. But remember, on top of that, we also have that sombrero that's tilted, right? And that kind of floppy thing. So imagine this pinwheel now folded into a sombrero that's kind of like a big floppy hat. This thing isn't flat. So as the sun rotates, this whole thing with the Parker spiral and everything ends up looking like that. Okay? And I probably don't need to show that. here we go. And here's a nice picture of it. And I will show a movie of this in just a moment. So that's a big floppy hat, very floppy. And you can see it's tilted. It's got these waves in it. It tilts. And it's got this spiral. So it's a pinwheel and a floppy hat. If a pinwheel and a floppy hat met in a bar, no. If a pinwheel and a floppy hat had a picnic, no. I don't know. But if a pinwheel and a floppy hat got together and had babies, I guess it would be the ballerina skirt, which is what we're looking at. Okay, and that's supposed to be a cute little planet here. I don't know if this over here, if that's supposed to be Earth or whatever. Kind of red to be Earth. Maybe it's Mars. Who knows? Oh yeah, look. Yeah, there are other planets. If you look closely, you can see, I never noticed that before. There are other planets in here. So it's trying to show you that there are other planets inside, and that's the ecliptic plane. It's actually quite instructive when I look at it. So you can see, if you see those white lines, you can see the orbits are being cut, right? It looks like they're being cut off by the ballerina skirt in certain places. And that's showing you how the planets, how as this ballerina skirt spins and this spiral continues to expand, how you can get through different parts of that spiral in different parts of that ballerina skirt, even though you're just sitting in the ecliptic plane in a planet, not just orbiting the sun, because this thing is blowing out past you all the time. Okay, so it's very variable. And here is the last chart that I did at the end of last course, and it was kind of just taking a part of that ballerina skirt and cutting through it. Okay, and I'll show you a movie in just a second that does exactly that. But if we were to cut right through that ballerina skirt, this is what we'd see, right? We have the sun right here. Back, right here. And you can see that little neutral line, the origin of that little floppy hat right there on the sun itself. Okay, and you can see it's not straight. And then as we extend that out into space, here's that neutral line extending out into space, becoming that floppy, ballerina skirt. Remember, the Parker spiral's on top of that doing this, but we've cut through it. Okay, we're not looking down at the North Pole, we're now looking at the sun from the side. The North Pole now of the sun, let me come back over here. The North Pole of the sun is right here. Okay, so we're looking at the sun in the ecliptic plane, kind of the same way we would look at it from Earth. Okay, and so all of the current sheet that extends out into space, you get fast solar wind streams as well as slow solar wind that's kind of sitting in the heliospheric current sheet, right? But you get fast streams both below and above it. And so as all this junk blows past you, right, if you're a planet, then you're going to see a lot of variability, right? And that's oftentimes how you end up getting these, these storms that really aren't, they're not transient. They're not, well, I can't say transient, right? They're not solar eruptions per se. They're just variability in the solar wind. But you really can get some pretty strong storms. As a matter of fact, just this last week, we had some very strong storming. We had, well, it wasn't moderate level, it was only a KP of 5, which is a minor storm conditions. But at high latitudes, it was quite beautiful. You had lots of aurora going on. We actually trashed the geo environment, for example. So if you go to my recent forecast, you'll see me talk about the Leo Mio geo environment, and you'll see the geo environment had some serious, significant surface charging, and then just a day or two after that, it started getting really intense internal charging as well. I think that might be calming down now, but yeah, the radiation belts don't like this stuff, not at all. So that's that bit. So we're gonna start talking about how that fast and slow solar wind slams into one another and what it causes, and I'll show a movie here in a second, but I'll pause for just a moment to, oh, thank you, new descendant. I will pause here for a second to take some questions. Auspicious Condor, good to see you here. I love seeing you. You always have fun, really fun comments on my forecast, so I appreciate that. How much is atomic number Z-grade shielding fabric per, oh my goodness, that's a different, obviously not for me. That Jupiter, yeah, that one planet, I was looking at it going, I think that might be Jupiter. Okay, I'm a new ham, glad I found you, Tamitha, great explanations of solar activity. Oh good, yes, congrats on being a new ham. I am reasonably too. I'm not really on the bands all that much. I'm trying to get more, but I have to take my general to be able to get really on HF and do skywave propagation, because right now I'm stuck as a tech. So I'm getting the lingo down, but I'm not very good at it yet. If a pinwheel, a floppy hat, and a slinky had a threesome. I love it. That's perfect. That's right. Oh my goodness. Okay, I hope Tamitha would know being a spacecraft charging mitigation consultant. Yeah, okay, I missed a question. How much atomic number Z-grade shielding fabric per square foot? Well, first of all, you would never use anything per square foot when it comes to spacecraft, because what you're trying to shield, oftentimes you try to spot shield, unless you're doing like thermal blankets, and that's something totally different. And really it depends upon the orbit that you're in, what type of shielding you need, and really what type of particles you're going to encounter. And that is a class, that's part of a class actually I'm teaching now. So we can get into that at some point if everyone on Patreon wants me to go into the magnetosphere and start talking about the Earth, the near-Earth system, and how crazy it is. Because space is not space is not space. Everybody thinks space is the same, and it really isn't. Something that lives and does very well in a LEO orbit, a low Earth orbit, can die a horrible death in GEO orbit, just because of the radiation differences, because of what they will do to paints and optical coatings and all sorts of stuff. And I mean, I can't go over that in great detail because, you know, some of that's proprietary. But I can go over the generalities, stuff that you can find on the web if you know where to look. I can talk about that stuff, and I can tell you the phenomenology as to why that happens. So that's a deep subject, Ben, and it's fun to talk about, but it is complicated. Okay. Let's see, what other questions? Oh, great explanation of the current sheet. You're very welcome, Leah. Oh, good, BG, you're new tech. Cool. How much will the grand solar minimum affect Earth's weather? Oh my goodness. You know, I don't know. I think it might already be. You know, it's hard to say though, because space weather is only so much solar phenomena, and then we turn around and we have cosmic rays as well, right? And they're different, right? So when you have the sun being extremely active, then you shield out the cosmic rays really well. But when you have the sun be really weak, you let in a lot of cosmic rays. And cosmic rays do all sorts of things to our ionosphere. It affects lightning, for example. Any type of radiation storm affects lightning. We're seeing that more often. And we also have cloud formation, right? And whether or not cosmic rays seeding clouds is something that cools our planet or causes a greenhouse effect, I don't know. I'm not a climate scientist, and I don't think there's enough work that's being done in that area yet. So some of the effects we think would happen may actually be the opposite. But I think it's a fantastic area of research that over the next, you know, let's pray 20 years or so, a lot more people are going to take up, because there's a lot of coupling between space weather and terrestrial weather, and we need to understand that better, especially as we become more spacefaring. So a lot of us, you know, both mainstream science are beginning to recognize that, and of course fringe science has been trying to do that for quite some time, and it's nice when they cross-pollinate. So we just got to keep at it, and we will eventually get these fields to come together, both terrestrial weather and space weather. We will marry them yet. We're working on it though. Okay, let's see. Can you fly through the Van Allen belts? Yes, we do it all the time. It's not some place you want to dwell in, especially if you're a human. There are some spacecraft that dwell there. GPS, for example, they dwell there. But we are very, you know, serious about understanding their dose and their dose rates. But there are some very dangerous orbits in you know, that we go through. Geotransfer orbit, for example, is not a fun one. And you know, there's a lot of stuff we could talk about. I'll get too far on a tangent if I continue too long on that. But yeah, again, I could do a class on that. So if we want to, maybe, you know, get your voice heard on Patreon. Any idea what's going on with the Kyoto Index? Oh gosh, yeah, we've got. I know there's a station apparently in Honolulu that's stuck, and with all the COVID nightmare going on, we haven't been able to fix it. It was fixed for a short while, and then it got bad again. But oops, my phone just buzzed. It's not. we just have to deal with it. It is very frustrating. I know that when this will probably only be in the real-time data, which is like level 1 data. Once, the preliminary data, once they go to, the final data, they'll clean it all up. But for right now, yes, there is an offset, and it's frustrating. And we all know about it, and we're all just kind of living with it. We're not super happy with it right now. So yes, it's not your eyes, and yes, you're not going crazy. It really is, there really is a problem. Oh good, new descendant. You use it in your university projects. That's awesome. I'm so grateful. Thank you very much. I'm flattered. How does a planetary index affect HF propagation if it does? The KP index, is that what you mean, the planetary? You mean KP? Well, the index itself doesn't affect anything, but if you're asking what does it tell you about propagation, it tells you a lot. Sadly, it doesn't tell you it in real time because it's a 3-hour delay with the KP. Your local K index would tell you a lot more. And you can get that off, depending upon where you are, you can get that from various magnetometer stations. Usually you have to look at it more as just magnetometer data as opposed to it being translated into a K index. But some places actually will give you a local K. And that will tell you stuff if you get, especially on Earth's night side, it can tell you a lot. The global index is a little bit more clunky from that point of view because it's averaging like 13 stations all around the world at different latitudes, mostly mid-latitude. And so it may not tell you as much about your local area. But again, that's another, I did a talk about that called All About Indices. That was another mini course I did, and I went into that in great detail. So please check that out. That's also on YouTube, All About Indices, and you'll see that. Okay, is there a possibility of a solar flare this year? Well, we're in what, September? Well, there's always a possibility, but do I think we're going to get a big one? I don't know. We've already had one this year. We had several M-class flares this year already, but sadly they went away. So we'll see. We'll see. Please get your general. Yes, I will. Probably not till next year though. I'm just slammed. I'm teaching 2 classes in Millersville this year, along with a ton of other stuff. So it's a little bit intense. And this will be the last question, then I will move on. Do sunspots help contribute to the tilting of the heliospheric current sheet, or vice versa? More like vice versa. What you're talking about is the solar dynamo. That's really what's driving everything, and the sunspots are a manifestation of that solar dynamo. As well as, and sunspots aren't the only things that have, variability in terms of where they come out in latitude and longitude. We have the same thing with filaments. We actually have the same thing there's similar things with coronal holes. They all move according to what the dynamo is asking them to do, and they all have a very systematic variability over the course of a solar cycle. And for that, I don't think I've done a course on that yet. So we'll have to. I touch on that in other courses I've taught, but not something that I've taught straight for YouTube. I might have something like that you could see a little bit if you go to Contest University. When I gave a talk at Hamvention in 2019? 2018? I can't remember. If you can go look, and I have something there that could maybe answer a few of those questions for you. Okay, guys, I think I'll move on. Thank you for the questions so far. And if I missed your question, please hit me with it again. And we'll talk about, I'll be sure to get to it. Okay, so let's talk a little bit about the basic solar wind. This isn't something, this is for those of you who like numbers. It's not obviously necessary for you to understand exactly what the numbers are, but for those of you who care, fast solar wind is typically between 400 and 800 kilometers a second. We typically call 400 kilometers a second, and this is at Earth at 1 AU. Okay, because the solar wind does change speeds depending upon where you are. So Earth is 1 astronomical unit, 1 AU. Okay, that's what we say in techno speak. And typically the slow solar wind is about 400 kilometers a second. Now, recently it's, when at solar minimum, it can go down even slower. But we talk about fast solar wind really getting much higher than that. 800 kilometers a second is not atypical. Right now we're only seeing 500 to 600 kilometer a second streams, but they will easily get to 800 near during the declining phase of the solar cycle. Fast solar wind is low density. Density always seems to go down, and we can have these structures last for weeks, and I'll show you that later on, what I mean by that. We have these coronal holes will stay on the sun, and they'll rotate across the Earth-facing disk, disappear because they're on the sun's far side, but they're very robust, and they stay. You know, they linger, and so they'll rotate back into view, you know, 27 days later, and so you'll get through a whole nother set of the same type of fast wind all over again, and it'll just keep happening. So that's what they say about what they mean by stationary. Now, slow solar wind, this is not happening from coronal holes. This is happening from the bright areas, mostly the heliospheric current sheet region, and it's only about 250 to about 400 kilometers a second. And yes, right now we're seeing slow solar wind at 250 kilometers a second. It's kind of sad. High density, I would say between 5 to 10 particles per centimeter. This is again at Earth at 1 AU. There's a higher flux. There's some differences in the helium content compared to the fast solar wind, but we typically get them from streamers. And if you look at the eclipses, the streamers are the high density, the things that look very white and very thick. As they come out, they don't look, they're not like at the poles of the sun where you see basically nothing. It almost looks like there's nothing coming out of the sun. But you see these big, thick things that come out on the sides, typically in eclipses or in coronagraphs. You can see those streamers. That's where the slow solar wind comes, for the most part. And again, Parker Solar Probe is changing that a little bit. But you can easily see just in spacecraft observations, sitting in the solar wind, you can easily see the differences between the two. And obviously, if you have such a big difference, then if you have, let's say, 250 kilometers a second solar wind in a slow speed stream, and suddenly you get hit with a fast stream that's 800 kilometers a second, you can imagine that's going to drive a shock wave. And sure enough, it does from time to time. Okay, and the Ulysses, oh, you know what I forgot to show you? It's right, I don't want to get into this yet. Before I do that, let me show you some of the cool movies. Whoops, come on. I'll just pull this down. You get to see my messy desktop here for a second. I'm not going to show that one, I'm going to show this one. Okay, so let me show you the Ballerina Skirt, because I want you to see, and I'll make sure it's muted. I don't think there's any sound, but I want you to be able to see how that Ballerina Skirt kind of moves out in the solar wind. So because I keep talking about this thing, and then I show you this stagnant picture. So let me get out of the way and show you this. And I'll stop it before it gets to the end because it goes beyond what we need. Whoops. But hopefully, so there's the sun, obviously. There's the Ballerina Skirt. Okay, look at that thing. Now the north and south, those spiral arms, that's the Parker spiral as you get close to the poles. This is one of the reasons why cosmic rays actually can funnel in to the Earth system a lot faster. Okay, there we go. Let me stop. Okay, that's a good place to stop. The spiral arms, or the spirals that you see here, the red and the blue, these are magnetic field, okay? Same kind of Parker spiral that we were talking about, but because the solar wind is now blowing up in the north and south in the poles, the Parker spiral becomes like a funnel at the high latitudes. This actually helps funnel in, believe it or not, galactic cosmic rays. This is why they actually enter the sun system, our solar system, much better this way from the poles than they do from the edges, which is coming in equatorially like this. Diffusing in this way is a lot harder for galactic cosmic rays, simply because of the magnetic shape and the way our shield looks, our sun's shield, into our solar system. The Ballerina Skirt, as you can see, remember we've now cut through part of it, and you can see it, you know, flopping like this. Floppy, 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 floppy. And as we get close to the edge of our solar system, it begins to really kind of cramp up together because it's because of the way the pressure is, the edge of our heliospheric bubble. And I'm not going to go into that part of it yet, but it gives you an idea that out here where Earth is, this is, you know, this is where we reside, and we pass through this thing all the time. Okay, so hopefully that gives you a better look at that. And then I'll get into the other movie in a minute. Talk about Ulysses. Come on, let me... Okay. So that was the basic solar wind types. Now you kind of saw with that ballerina skirt, every time you were inside that ballerina skirt, that was where you get the slow solar wind. Every time you were out of it, that was where you'd get the fast solar wind. And really where we learned all of this, not all of it, but a lot of it, was through the Ulysses mission. This was a mission, if I stand over here, this is the mission where, you know, basically everything prior to it was sitting in the ecliptic plane in this green disk, okay? Ulysses actually went out of this disk. Do you see this elliptical orbit? Went all the way around the sun and did it, oh my gosh, almost like over basically an entire solar cycle. It was wonderful. And I'll show you a neat movie that kind of summarizes what it found. The neat thing, one of the neat things is that it went over the poles in 2000, 2001, which is right near solar maximum. So it saw some really cool stuff that we hadn't expected to see. And thank goodness for that. I'm not sure we actually planned for that, but that's the way it ended up happening. And one of the things that you see, and I think I've got a lot of stuff on this plot. This is a very interesting plot, and I'll show you the movie that goes with this in just a moment. Ulysses it definitely told us or taught us that the solar wind varies with altitude or with latitude, not just with the solar cycle, but also with latitude as you move over the sun. And what you're looking at is a polar plot. Okay, so obviously the sun is in the middle. Okay, and if you see, there's an axis that goes up here. This is, it says 500 and then 1,000 on this axis. If I get my hands in the right place, so 500 here, 1,000 here. Same thing on this. If I go south, let me just go to this one. Okay, it goes 500 and then 1,000. Hopefully you can see the 1,000. And then it also goes out this way and out this way. Okay, and the numbers are 1,000 on this side and 1,000 on that side. Okay, so basically what it's trying to tell you is that no matter which way you go around this clock, okay, because we're going to call it kind of like a clock, no matter which way you go around this clock, it's going to give you, if you see a line, it's going to say how far out is it? Is it 500, 1,000, or what's the amount? In this case, we're going to talk about solar wind speed. Okay, so what it's basically saying is that for latitude, like if you're looking straight at the North Pole, or you're looking at this wind that's coming out of the sun's North Pole, it's almost completely 800 kilometers a second. Right here, let me get to where this line is. See this right here? It's showing about 800 kilometers a second all the way till you get to this latitude here. Okay, and this latitude is, I don't know, what does it look like, about 30 degrees, 40 degrees, right? Less than 45, because 45 degrees is halfway. If I put my hand right here where the sun is, that'd be 45 degrees. 45 degrees this way and 45 degrees this way, because it's a 90-degree angle. Any of those of you who actually know geometry. So here's 45 degrees north, 45 degrees to 0, because this would be 0 degrees latitude. This is 90 degrees. So at about 40 degrees or so, maybe 30 degrees, is when you start seeing that solar wind that was going so fast up here. Watch it at 30 degrees-ish, jump down. Shoot. Do you see this stuff down in here at these low latitudes? This is solar wind around 400 kilometers a second. This is what Ulysses saw. So as it went down to the lower latitudes, in through 0, it saw really slow solar wind. And then once it got to 30 degrees south-ish, give or take an ish, it jumped back up again. Look how fast the solar wind is again. Back up to 800 kilometers a second. Oh my goodness. And all the way down to the South Pole, right? And all the way around. Don't worry about the colors yet. We'll talk about the colors in a second. All the way around. And then, as Ulysses began to go into the lower latitudes again, it was doing it on this side. It was doing it at a different time in the solar cycle, actually during the declining phase of the solar cycle. And this is why you started seeing this stream structure. You started seeing fast wind, slow wind, fast wind, slow wind, fast wind, slow wind, all the way down until you got to really low latitudes again, right? So now we're going through 0, near 0 south, right? Maybe 10 degrees south. It got really quiet and really slow solar wind. If I put my hand out here, right here. There's the slow solar wind again. And as it moved up to the north, maybe 10 or 20 or 30 degrees north, it started seeing that stream structure again. Look, fast wind, slow wind, fast wind, slow wind, fast wind, slow wind. So it kept going through these coronal holes. The sun would keep rotating, and it would hit a coronal hole, and then it would hit the heliospheric current sheet, and hit the coronal hole, and hit the current sheet. So you'd get the fast wind, slow wind stuff, until you got about 45 or so degrees north, and then it was all fast wind. Okay? So the reason why one side of the sun looks different than the other side isn't because one side of the sun is different. Remember, the sun's rotating all the time. This is actually showing variations in the solar cycle. Because it took a while for Ulysses to get around. Ulysses, it was out, I think it was like at 2 AU at some point. It was almost twice the distance from the sun to the earth at one point. Now, the color codes are just simply the magnetic field direction. So in this case, inward, the solar magnetic field was pointing inward toward the sun, and out with the red, it was actually pointing outward. So I should say outward this way and inward this way. But it was just showing what the polarity of the magnetic field was. Okay. Now this plot, oh no, it didn't. Okay. Let me show you a really cool movie at this point now that correlates this. It actually shows how the solar cycle was affected this measurement. Okay. But here's what you can see here. I can get out of the way. So here's Ulysses. Here's that same polar plot. See that? So the solar wind speeds. Now there is the interplanetary magnetic field and the solar wind. Look at the plots you see there. And what happens is that when the sun rotates, when the sun's magnetic field flips in its solar maximum, everything begins to change. Okay, it actually all goes kind of slow, and you're seeing the fields beginning to flip. When you have a multipolar sun, everything's just a mess. And then as the field redoes it, whoop, sorry, I'm getting a call. As the field is remade, then the magnetic field flips. I'll do that again. Sorry, because I got a phone call right at that time. Not an important one. Let's start that again. Try that again. So again, here's that polar plot, okay, solar wind speeds. And that's what it looks like during a solar minimum. You've got really slow solar wind at the equator, and you've got fast wind at the poles. But as you start moving toward solar maximum, the solar wind becomes a jumble, becomes a mess. The dipole field disappears, all the solar wind gets messy. You can get fast solar wind and slow solar wind at any location because you get a multipolar sun, and there's showing the fields flipping. And then as they flip and the dipole field reforms, notice now blue's on top, red is on bottom where it was the opposite before. And now you've reformed it where you get the fast solar wind in the north and the southern pole, but you get the, let me zoom it back and I'll freeze it. You get the fast solar wind at the north and the south pole, but now the interplanetary field, the solar magnetic field directions have switched. What was outward is now inward. In other words, what was blue is now red, and what was red is now blue. But that's kind of what Ulysses taught us, was that not only do you have a latitude variation with the sun, where during solar minimum, for example, it looks this beautiful, where you've got fast solar wind at both poles and really slow solar wind in the ecliptic plane, where all the planets are. But during the solar cycle, everything gets crazy, especially during solar maximum. You can get fast wind streams anywhere and everywhere, and they don't really last all that long because all the coronal holes in those regions become those little islands. And so they become, kind of jumbled. And so the solar wind in general kind of slows down a little bit. And then as the field flips and that dipole field begins to reform, then the solar polar field changes, the global field of the sun changes direction. But you then reform those really pristine fast and slow wind coronal holes at the northern pole and the southern pole. And as a matter of fact, a savvy scientist now, as we know, a savvy scientist can look at the sun and look where the coronal holes are on the sun and tell you what part of the solar cycle you're in. There may be a little bit of discrepancy with, like, is it the rising phase or the declining phase? But they'll be able to tell you if it's near solar minimum or solar maximum just by looking at where the coronal holes are on the sun, because we know the dynamics so well. So hopefully that helped answer or clarify some of this that we're talking about. And you'll see a little bit more of that here. Now, I guess I can tell you for those people who are interested, let me just make sure, did everybody get that? Hopefully everybody understands. Yes, the Earth is going through a pole flip. It's a lot slower though. So hopefully everybody understands that. I don't see anybody saying no, so that's a good thing. For those of you who are interested in the heliospheric current sheet, it actually can look, this is actually a superposed epoch analysis. That means that they've layered a whole bunch of them on top of each other. All these heliospheric current sheet passings, and they've laid them on top of each other to kind of get an idea of what they look like in aggregate, in a group form. And they find that yes, as you pass over the heliospheric current sheet, the density really does go up. The velocity of the solar wind really does go down quite a bit, and the temperature, there's always a spike in temperature as you move away. It gets kind of cold, but then you get typically some type of stream interface afterwards that causes the temperature to change. I'm not going to go into the details of that, but there are a lot of studies on heliospheric current sheets if you're interested. Sometimes people mistake them. Okay, enough. Sometimes people mistake them for solar eruptions. And part of the reason for that is because you end up getting something called stream interfaces, and we'll talk about those in a minute. This behind me is another view, and just in case those of you who wanted to see what density looked like. So you've got that same kind of polar plot, but now overlaid in green. I think there's a whole bunch of stuff that's on top of this. Yeah. Don't really need all that. Blue will be inward. Okay. Just focus on the green now. The green lines, same kind of polar plot, but notice that in the poles or near the poles, the density is really low. The solar wind density is low, which is consistent with fast solar wind. In the ecliptic plane, the density is really high, right? And in this region of slow solar wind, the density goes up. And again, this was Ulysses measurements, and look at the solar cycle change. During a period of higher activity, we weren't just in solar minimum on this passage. So you saw that stream structure, and that's why the density is going high, low, high, low, high, low. Same kind of thing as the solar wind went high, low, right? So this side is beautiful solar minimum kind of configuration, and here is a more active configuration, not quite solar maximum, but nonetheless, it was either ascending phase or descending phase, I forget which. But it gives you an idea of really how variable our solar wind is. Okay. And do I need to show this? This is maybe a little bit redundant for you guys now at this point. Yeah, this is I showed this pretty well with the movie, but again, this is nearing solar minimum. You can see how the high wind going into slow solar wind, going into high wind. So you had fast wind during, at high latitudes with slow solar wind during, at the low latitudes, and that's during solar minimum. Around solar maximum, it's a mess. And look at the red and the blue, right? The red and the blue colors. You no longer have, red field in the north and blue field in the south. You have it everywhere. That's the multipolar sun. This is what happens to our sun when we have no dipole field, right? It's not that the sun doesn't have a magnetic field. It's not that the sun doesn't have, something that's generating a magnetic field. It's just the dipole, the pretty ordered dipole field component goes away. We're going to have something similar to this happen as the Earth's magnetic field flips. It's not going to be quite this messy, but it's going to be messy. And boy, that's going to be fun for space physicists, because we're going to try to understand whether or not we're going to even have radiation belts. I'm not sure we will. There's a good chance all that order is just going to disappear. And it's gonna be a very interesting time for spacecraft. Not sure how we're going to deal with it. Not sure too many people have studied that yet. A lot of people from UCLA have, but not from the point of view of applied physics. So the Air Force or the Space Force is going to have a lot of fun coming in the next 300 years. And again, this is kind of another way of looking at it once again, emphasizing exactly the same thing but in a different way. So here was Ulysses' first orbit, during solar minimum. You can see how beautiful it was. Ulysses' second orbit during solar maximum, and Ulysses' third orbit during, as you started nearing solar minimum again. And down here is the sunspot number, just to, that's in the black. The red line is the current sheet tilt. Don't worry about that too much. That's, we talked about the dipole field tilt. That's what that same thing is. How tilted is that sombrero? And it gets really tilted during solar maximum, yeah, because that's when we get all those magnetic islands. It tilts so much that it basically breaks. You can only tilt the dipole so much before it, kind of is unrecognizable. But it shows you how incredibly variable our star is and how we have to be very careful, both in latitude and in solar cycle, when we take a look at the solar wind and we try to understand how it's affecting, different bodies in our celestial sphere. And now let's talk specifically about how this fast wind and slow wind interact. Usually in class I would say, how many people have heard of a stream interaction region? But I don't know, I can do show of hands, but I'm not sure that works quite so well here. Here is the origin, though, of fast solar wind streams and basically the solar storms that come from the interaction of fast and slow solar wind. If you think of yourself in a lake, and if you were to, you could either think of yourself being a boat in a lake, or if you drop a stone in the water, either way. What happens is that you start moving water in front of the stone or in front of this boat, and it's pushing into either still water or very slow moving water ahead of it. And what happens? You form a wave, right? Because you get compression. You get this fast water slamming into the slow water ahead of it, and it compresses everything up and creates this nice, what we call compression region. Same exact thing happens with the Parker spiral when you have fast solar wind streams slamming into slow solar wind streams ahead of it. And if I stand, let's see if I stand over here. No, let me stand over here. This is trying to diagram exactly that, and hopefully I can make this clear. Again, this is the Parker spiral. Now, if you recall, during our last class, the Parker spiral, how tightly wound those Parker spiral arms were dictated by how fast that solar wind was moving. So if the wind was moving very, very slowly, then the Parker spiral arms, the pinwheel arms, were very, very tightly curled. But if the wind is moving out very fast, well, the sun isn't rotating very far before those parcels of solar wind are able to get really far out. So therefore, the spiderweb magnetic field that's threading them isn't curling so tightly. It's a looser spiral, okay? It's a looser pinwheel, and we actually can show what happens just with the magnetic field, the Parker spiral arms of the magnetic field of the solar wind. We can show how that creates compression regions. If you take a look here, we've got the sun, we're looking down at it from the North Pole, right? And it is rotating like this, that way, okay? So let's just assume we have this part of the sun has slow solar wind coming out of it. This part that has the fast solar wind, that's a coronal hole, right? And it's got some fast wind coming out of it. And then ahead of it, it's got some slow solar wind again, okay? So that's a very common configuration on the sun. And the slow solar wind that's on this side, it's got these tight Parker spiral arms, right? Because it's slow. That pinwheel is very tightly curled because the solar wind is not moving out very far before the sun is able to rotate quite a bit. So it's really, as it lows out really slowly, that Parker spiral that sun is rotating quite a bit. So that source region is way over here, and it's really got a strong curve as that thing comes out. Whereas with the fast solar wind, that thing's moving out very fast, and the sun isn't rotated very much. So that Parker spiral curve is kind of softer, it's gentler, right? So that's what we're seeing here, is in this slow solar wind, we're looking at the Parker spiral kind of being really tight and really coming in. But when we get to that fast solar wind stream, that solar wind, the Parker spiral isn't nearly as tight. And so what happens? The field lines kind of slam into one another, they converge. In this region, right, because it's also showing where those parcels of solar wind are going, in this region is where you get that compression. This is that wave that we were talking about with the boat plowing through the water. That compression does happen. This, believe it or not, the solar wind is considered a fluid. It's a plasma fluid, but it's still considered a fluid. So it acts very much, you can actually think about it kind of like water, like a river. And you get this wave slamming in, that's forming from the fast wind slamming into the slow wind. We call this compression region, okay, a stream interaction region. You will see it oftentimes being called an SIR in science vernacular, or a CIR. The only difference between an SIR and a CIR is an SIR, it's the first time you've seen it. It's a stream interaction region. A CIR, a co-rotating stream interaction region, meaning you've already seen it one time. It rotated once around the sun, and then the fast solar wind is back. The coronal hole survived its far side passage. It's back in the front again, and it's Earth side, and now this is the second or more times you've seen it, and now it stops being an SIR and starts being a CIR. The terms, sadly, are used interchangeably, so don't be confused if you happen to be reading something and you see both SIR or CIR being used. There's no fundamental difference other than just record keeping, that yes, we've seen this one before. Okay. At any rate, so you get this compression wave in front, and if the fast solar wind is strong enough, is fast enough, and the slow solar wind is slow enough, this compression region, this wave will steepen, what we call steepen into a shock. So you can actually get a shock wave at the front of this thing. And as a matter of fact, as these stream interactions, as the solar wind moves outward in space, the solar wind picks up speed, continues to, at least for a while. And what ends up happening is that right at where Earth is, right at 1 AU, we are right in a transition zone where a lot of these, the average stream interaction region is just beginning to steepen into a shock, just beginning to. So sometimes we'll see these SIRs that have shock waves in front of them, and sometimes not quite, because it depends upon how strong it was. So we can't always expect to have a shock wave in front of these things, but sometimes we actually do see it, especially when the sun is extremely active and these coronal holes are really shooting out some fast solar wind. So after that, you again get a rarefaction region when you have, once again, slow solar wind and that tight Parker spiral again. So the spiral, you can see the magnetic field is really separated, and that means it's a rarefaction, meaning that it's a lot less dense. So that is a typical solar wind stream, and these things will, these things will actually cause solar storms at Earth. And oftentimes they'll actually mimic what it's like to have an actual solar eruption, because oftentimes these solar eruptions, they have a shock wave in front of them, and they have a bunch of dense, stuff behind, that is the actual eruption, the actual CME or solar storm. And it's the same kind of thing with these stream interactions, right? You get sometimes a shock in front, and then you get this really compressed region of plasma. And so they can actually drive similar storms that just like what we see with coronal mass ejections and those types of things. So you don't necessarily have to have any type of eruption from the sun in order to get a big storm at Earth. And that's something that a lot of people don't realize. It's like, well, wait a minute, the sun, there was no flare, there was no CME, there was no nothing. How can we actually be having a geomagnetic storm right now? Well, that's why, is we're dealing with fast solar wind. And as a matter of fact, some of these can actually have both a leading shock and a trailing shock, because you can actually get a shock wave when you have what we call a forward shock, when you have the fast solar wind slamming into the slow solar wind ahead of it. And then, believe it or not, you can actually get a reverse shock when the fast solar wind dies down and the slow solar wind takes over. So sometimes you'll actually see two shocks. Typically the leading shock is well formed, the trailing shock not so much. But you see that far more better formed out at further than Earth. So, and I might even have something like that. Because remember I was telling you about how the solar wind continues to pick up speed for a while. I think I have in this chart deck, I think I have some solar wind that actually, like at Jupiter or something, that shows a leading and trailing shock, and you can see it quite well. But for those of you who actually know what solar storms look like when you're looking at solar wind data, like right out in front with our solar wind monitors, for those of you who know what they look like, I'll show you how similar these things are to what ejecta look like, what coronal mass ejections look like. So here's some solar wind data, and don't worry, there's not going to be a test or anything. So if you don't get it, don't stress. I'll show you down at the bottom. Okay, now this is a time series, so time goes this way. Okay, and each one of these panels represents something in the solar wind. I'm not going to get you to look at every panel because it's not important. What I will get you to look at first of all, though, is the pressure. Look at the pressure here. It goes way up as you go through this stream interaction region. Remember, we were talking about that compression wave? That's showing you that compression. Okay, and before it there was nothing. That's the slow solar wind, very low pressure. Okay, and in the back of it, not so much pressure either on this side. But in the middle of this thing, where that big pressure wave is, you can definitely see how much it goes up. Okay, the top panel up here, this is velocity, or speed rather. You can see before the stream interaction region, it's really low speed. Looks like it's, well, not that low. It's like 450 to 500 kilometers a second. It's low enough. Okay, and then as you begin to go through this compression region, look at the speed begin to jump up. Tick, 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 tick. Once you get to here, this is the high-speed stream that's following it. Okay, you're almost at 750 or so kilometers a second. So you go from 450 to 750. That's a pretty decent jump. And they do have it labeled. It's not labeled very, I mean, the shock isn't very strong. That's where this brown line is. It's showing the forward shock. And it's showing where the heliospheric current sheet is. Don't worry about all the details. But that's remember, you're crossing from fast or slow wind into fast wind. And remember, we were talking about crossing through that heliospheric current sheet. You do cross that sheet, and you can actually see it because you can see it in the density. The density goes up. And then you end up getting the reverse shock over here. Or no, the forward shock. No, it is. It's a reverse wave, they're calling it. Because at Earth, it's not really, they're not really well formed. And so we've got it kind of mapped out where if you are a spacecraft over here, that's this cute little sun thing. If I can get to it. Deet, 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 deet. Right here. I know this is a little bit complicated. I used this for the Millersville course. I wanted my students to understand that these structures, because I taught them how to look at, and I've taught you guys too, how to look at solar wind data and be able to model, be able to tell what the orientation of a big coronal mass ejection looks like if they come out as a solar slinky. We talked about that in one of my CME courses. And so we looked at solar wind and the solar wind magnetic field and structure of these big transient structures that come off of the sun look very much like this. So I wanted to make sure that they understood that not everything that you see in the solar wind that has like a big compression wave and stuff like this, that looks kind of like this, is a coronal mass ejection. Because this isn't. This is just solar wind. And yet, it's pretty impressive. I mean, even us scientists sometimes get upset because we end up, you're not upset, we get confused because we end up trying to figure out if there's a coronal mass ejection embedded in one of these structures. At any rate, okay, so if we're looking at the spacecraft trajectory, you're going to have this big, Parker spiral stream structure move over the spacecraft, okay? And so what they're doing is they're mapping out the front end. You can see the brown arrow mapping out the front end of this thing. Okay, that maps to the forward shock that you see behind me. Well, on this side, I guess. The forward shock you see behind me, and I'll move out of the way in a second. And then if you go to the blue, you can see that's mapping to the heliospheric current sheet as you're crossing through it. And then the trailing edge, that's the trailing wave as you go back into slow solar wind. And when you actually fly through it, if a spacecraft actually flies through it, this is what it looks like in the time series. Crazy, huh? Pretty nuts. But you can see all sorts of changes in temperature and density. This temperature is over here, is this plot. Density is this one where you see the peak right at the heliospheric current sheet, where the blue is. And then don't worry about this stuff here, this mess. This is the orientation of the magnetic field. Don't worry about that. It's done in angles and it's complicated. But you can actually see, again, with the speed of the solar wind, that's this top panel. Whoops, get my hand in the right place. You can really see how that speed starts off as being slow, and then as you move through it, you get to fast solar wind. And it's not the fast solar wind that causes the big storm. It's what we call the stream interaction region. It's the region, it's where the two are interacting, where the fast wind is slamming into the slow wind. We have that special thing, we call that an SIR. That's what looks like, what mimics a solar storm. And then the fast wind is like a fast wind chaser. Oftentimes in my forecast, you'll hear me say that. We'll be like, well, we're going to hit that stream interaction region, we're going to have this fast wind chaser. And that fast wind chaser then keeps us storming. It's the SIR that gets us there, and then the fast wind, because it's so fast and it keeps feeding. It's like you know, trying to drink from a fire hose. Because the water's coming out so fast, it keeps that storm going. Okay? And that's how those stream interactions work. And here is, you know, here's an example at Ulysses. That I don't remember what latitude it was at, but you can see these things again all over, and I won't spend much time here. Let me stand on this side. They look a little bit different at higher latitudes, but you once again get a forward shock and a reverse shock, and the stream interaction region is in the middle. Okay, that's that whole region, and that's where you see all the magic happening. Okay, and we have all these different markers that tell us about it. Oh, and we have one at Jupiter. Look at Jupiter. So even as we go further out, and see, you can actually see how the shock waves are formed better. See, it's much clearer at Jupiter, isn't it? Can you see that? You can really see where the start and the stop is of the interaction region, because, like I said, as we move further out, the solar wind gets faster, and there's a lot of other changes too. But you can see these shock waves a lot more clearly, and so the stream interaction regions become a lot more clear in time series like this. And let's see, SIRs and CIRs observed by Voyager. Oh, goodness. Yeah, I want to be very careful if I start going out too far, because then I'll have to start talking about the heliosphere. Right, this is Voyager near the edge of the heliosphere. Believe it or not, stream structure actually does continue to exist. The solar wind, of course, weakens dramatically, and I don't want to get into that too much, because otherwise it'll lead into my discussion of what do we do when we get to the edge of the heliosphere and the solar wind kind of peters out. It does peter out. But you still can see these interaction regions, and they actually call them MIRs at this point. They start becoming merged interaction regions, because what happens is as the solar wind gets closer to the heliosphere, it actually begins to slow down. And these stream interaction regions kind of pile up on one another. And so one will slam into another, and then that will slam into another, and it strengthens them and makes them much more visible out here at least a few years ago at Voyager. Voyager's now, you know, out beyond our own solar system. So it's not seeing these structures anymore, because it's beyond the influence of our solar wind. But a few years ago, it actually was. Let's see if they have a year on this. Oh, I can't read it. Sadly, this observation may have been, gosh, it may have been as much as 5 or 10 years ago. But as our solar wind begins to slow down as it gets closer and closer and closer to the galactic wind, because the solar wind has to stand off that galactic wind, and at some point it begins to not be able to. That gets to us to the point where we're a termination shock, where everything kind of stops. Everything compresses at that point, at that region. And so all the stream interaction regions kind of come to I don't want to say a halt, but almost. And so they start looking very, very different. But we are actually still able to see them, and that's what they're trying to color in here. You can still see forward shocks and reverse shocks. You just don't see the CIRs nearly as well. You can see, I mean, you basically can only mark it so much by seeing slight fast wind stream as you go through this thing. You can see the forward and reverse shocks, and those are the big indicators. But the SIR itself becomes harder and harder to see. But it's cool that we can actually watch them all the way out. And then I wonder if we've already kind of covered this. I guess, yeah, we've already pretty much talked about this. But what was neat about this particular plot was that the professor who did it was actually trying to draw in. We were talking about these forward shocks and reverse shocks, and how they kind of, if you were to go back to the solar source regions and map them, it's kind of neat to see. Granted, it's not done all that well, because the neutral line, for example, is actually going over the coronal hole oopsie, that doesn't happen. The magnetic field would bend around that coronal hole. It would not cut through it. So that's a little sloppy. But what I liked was the fact that he took the time to try to show the slow solar wind in the red arrows coming out in a tighter Parker spiral. Kind of cute, huh? The fast solar wind coming out of the coronal hole. Okay, so see the red stuff is coming out. The red solar wind is coming out of a brighter region. It's not supposed to be coming outside or coming out of the coronal hole itself. It's just alongside it. So that's showing slow solar wind. The blue line is showing the fast solar wind coming out of the coronal hole, and in a Parker spiral field that's less curved because it's faster. And when they collide, blue and red collide, you get both the front, the forward shock. That's the front thick black line right here. I'm trying to draw. I can't draw very well. That's that front black line, and then you get the reverse shock on the other side, if I can get there. And the stream interaction region is all this area in here, right? In front is slow solar wind, behind is fast solar wind, and actually no, inside is fast solar wind. And then then you have the full stream, depending upon how I don't know how far out they're going to show this, but and then they're trying to show a spacecraft cutting through that as you go through it. And that's kind of this same kind of diagram here. Instead of looking at the sun, the way the Earth would look at it, now you're looking down at the sun from the North Pole. And he was drawing kind of the same thing. But I thought this was kind of cute. I probably will replace this diagram with one that's drawn better, especially with a neutral line, because the neutral line really bothers me. Because I don't want anyone to think that a neutral line would cut right through. I should say maybe that's the geographic equator and leave it at that and not talk about magnetic field, but everything else is magnetic field, so it irks me a little bit, so I need to improve upon this, but it's kind of the idea. So I'll pause here before we go into what these types of storms and what kind of these types of streams do to Earth, and get into just a little bit of the fun stuff. And I don't think I have that many more charts other than supplemental stuff, because I don't think I put in a lot about, I didn't show, I didn't include specifics with actual spacecraft. I probably should have for this class, but I might show that next time. Let's see, we're almost 1 o'clock. I've almost done, it's been an hour and a half as it is. So let me pause here, see if anyone has questions, and see how well I've done so far explaining the second half of this class. Is Jupiter a failed sun? I wouldn't call it a failed sun because I don't think it was quite large enough. It needed to be a little bit larger in order to ignite. I'm not sure a star can fail. Once it becomes large enough, it will collapse in on itself and it will ignite. So how long that lasts, I don't know. I'm not an astronomer or an astrophysicist, so I don't study the sun that way. Now, being a space weather person, I look more at the transient stuff coming off of the sun. I don't do solar physics nearly as much as astronomers and astrophysicists do. Let's see. In the film 2010, Jupiter Became a Star. I'm not really sure how that could happen unless something, I didn't see the film, but unless something very massive. I think Jupiter had to be something like 4 times more massive than it is in order to ignite. But don't quote me on that because I'm not sure. Have the moon phases changed any in the past couple of years? I asked because the moon view seems to have changed across the northern U.S. Not that I know of. The moon is in tidal lock with Earth and has been for, a very long time. So I don't think the moon has changed. I wouldn't think that was that should be an issue right now. What conditions are necessary to cause a Carrington event? Well, believe it or not, low activity solar cycle is probably the most likely candidate. So what we're dealing with right now, as a matter of fact, this past solar cycle, we've had 2 to 2.5, because there's one that was a near Carrington class event that we argue whether or not it's a Carrington event because we didn't see it at the apex. We only experienced it through the flank, through the edges of it. So it's hard to tell if it really was Carrington class or not, but it was close. And if I count that one, then we saw 3 Carrington-class events this solar cycle, this past solar cycle. 2 of them, for instance, for example, were during 2017, and then another one was during the 2012, that famous one back in July 2012. But there were 2 during the 2017. Remember Hurricane Harvey and Irma, and the largest solar flares of the solar cycle occurred in September of that year, and we just got lucky that the 2 massive events that occurred, the 2 massive solar storms that were launched at that time, one of them clipped Earth. As a matter of fact, the one that clipped Earth was when we had a big flare that was actually a big flare, and at the same time we launched a huge coronal mass ejection, and it was the active region that did it was actually becoming farsighted. It was actually being occulted. It was actually pointing like this way. If you are Earth, it was actually facing this direction, and it fired off a massive solar flare, and it fired off a massive coronal mass ejection. The thing was so large that it actually clipped Earth. So imagine me firing a gun and having the bullet be so wide that it actually hits you. That's how big this event was. It caused a G1 level storm at Earth for about 6 hours. I couldn't believe it. It caused a radiation storm that was seen at Earth and at Mars, which was all the way around the other side of the sun at the time. It was a very scary event, to be honest. But we had 2 from that particular region. One was farsighted, so we didn't see it at all, and then the other one was the one that clipped us. And then the one in 2012. So 3 Carrington-class events, and a lot of people believe, and this is why I need to do a solar cycle class, is because we believe it has to do with the hemispheric asymmetry of the sun right now. During these low activity cycles, the magnetic field of the northern and southern hemispheres is not in sync. They're arguing with one another, and that arguing means that the activity level, I don't want to say level decreases, the intensity decreases. So you have, when solar storms are launched, oftentimes the average intensity of these storms are low, or lower than you would get with the much higher activity cycles. However, the complexity of the magnetic field on the sun is increased quite a bit. So every now and again you will get these active regions that are unbelievably complicated that we don't really see nearly as often during cycles that are high activity cycles. The magnetic field is not quite as complicated. Now, you get more intensity that way, but you get less complicated magnetic field. And when you get complicated magnetic field, then you can unleash a ton of energy in a transient. So that's when we get these superstorms, these superstorms, Carrington class. And I won't go into that too much. It has to do with superposition and stuff like that, but I won't go into that right now because that's a little bit beyond the scope of this class. But hopefully that answers that question. And yes, I will do a course on that reasonably soon. Let's see. That is somewhat disturbing. Yes, I agree. Yeah, cycle 25 Terminator. Right. Somebody knows Scott McIntosh. Sir Scott Ferguson, knowing Scott McIntosh's and UCAR's work, because they're talking about exactly that. They do probably the best work on the magnetic asymmetry of the hemispheres of the sun. Let's see, any other, during the 22-year solar cycle, how many solar maximum and minimums are there? During the 22-year solar cycle, well, basically the 22-year cycle is the same thing as the 11-year cycle, except the 11-year cycle only talks about going from a maximum down to a minimum and back again. The 22-year cycle is going from a maximum down to a minimum, up to a maximum, down to a minimum, and then back to a maximum. And the reason why they want to do that so much is because in the first maximum you have, let's say, let's say the magnetic field of the sun is north, northern pole is north, southern pole is south, let's say. Let's talk about it, dipole magnet. You have a north pole and a south pole. Let's say in one cycle you have a north pole where north is north and south is south. As you go to solar minimum, right, the dipole field disappears. Gotta be careful. As you go to solar maximum, the dipole field disappears and then reforms. But when it reforms, now the northern pole is south, the southern pole is north, okay? And that would be an 11-year cycle, right? But the magnetic field is reversed compared to what it was the cycle before. So if you want to add the magnetic field back in order to complete one complete polarity reversal where you start north-south, go south-north, and then north-south again, you now have to go through, once again, another solar maximum to get that dipole field to go to 0, and then have it reform, and now the northern magnetic field is north again, and the southern magnetic field is south again. So that's why you can say an 11-year cycle is really a 22-year cycle if you include the geomagnetic, or the sun's magnetic field, the global polar field of the sun. And it just makes you have to go, from north-south, south-north, and then back again. That's really the only difference. So from that point of view, I guess you have 2 solar maxima and 2 solar minima, right? It's just twice as long. But they're really the same cycle. They're looking at the same ideas. It's just, do you include the magnetic field or do you just include solar activity? That's the difference. Hopefully that answers that question. What about our binary star? Our binary star? What do you mean binary star? We have one star in our system. I pray we aren't in a binary star system or we're in real trouble. Let's see. What effect does gravity have on the solar wind? It's escaping. It's got escape velocity. I mean, if that's the whole difference between the solar corona and the solar wind. The solar wind is the part of the solar atmosphere that said, "Ha-ha, I'm faster than you can keep me in." So it's actually the part of the atmosphere of the sun that's actually managed to escape the sun's gravity. So from that point of view, the gravitational pull from the sun, it actually managed to beat it. Hopefully that answers that question. Of course, there is gravity that's going to be interacting with all these particles, but remember, the solar wind itself is so incredibly vacuous that for one particle to touch another, to even touch another particle, to even collide with another particle, those particles have to travel basically the distance from the sun to the Earth. That's what we call the mean free path. How long does it take for one particle to actually even have a chance of interacting with another particle directly by collision? It has to travel that far. So that tells you how vacuous the solar wind is. It really is connected by these spiderweb magnetic fields. The magnetic fields and electric fields are really the spiderwebs that kind of keep all of this plasma, all of this solar wind talking to one another. You jiggle the magnetic field over here and the particle over here on the other part of the web, wiggles. That's how they talk to each other. It's not that they collide with one another, because this is a collisionless plasma in space. So gravity has very little to do and interacts very little with, or has a very small force on these particles, especially when you're considering most of them are, ionized protons and electrons anyway. I mean, gravity doesn't really, these are quantum mechanical things pretty much. that quantum mechanics probably plays a much larger role than classic gravity. So hopefully that explains that. But yeah, it's a very, very vacuous plasma. Oh, you're so welcome, Brian. I'm glad you're getting you're getting good stuff out of it. Earth will be a nice ash-filled environment soon. Get ready, peeps. Not from the sun, let's hope. I really hope not. I don't try to be any fearmonger. So anybody who's getting space weather information that is telling them that our star is going to destroy us anytime soon really is watching the wrong channel. We've lived with our star for, as long as humans have been alive. I think we're going to be okay. And, as far as Carrington class events and what they will do to our technology, we're getting smarter. We're not going to have buildings catching fire, stuff like that. We don't have, thousands and thousands of miles of unbroken power lines, right? Power grid companies and utility consortiums have gotten very smart, especially after the 1989 event. That really woke us all up. And we have lots of ways of doing mitigation. Now, granted, we are stupid in some areas, and we will still make a lot of mistakes, and we will still run things to failure that shouldn't be. And I won't go into the details of that right now. But that's just human nature. So we're going to learn by doing things wrong. But whether or not people believe that a Carrington class event is going to set your pacemaker on fire and cars are going to be stopping running, simply because of the EMP. No, it's not going to be like that. It's really not going to be like that. As a matter of fact, if you live in America or anywhere at mid-latitudes, you actually have less of a chance of getting hit by an EMP from a solar storm, an Earth's solar storm, than you do if you're at really low latitudes. The EMPs are actually worse at low latitudes than they are at mid-latitudes. We have bigger issues with GICs, which are the induced currents in the power grid. So the neat thing about space weather is that it's very much like terrestrial weather in the sense that there are all these locales, and depending upon where you live, that dictates what your space weather susceptibility is. And luckily, it's not the same susceptibility all over the entire planet. So people keep thinking, oh, it's going to be one big thing and everything's going to be out the same way, the same time, the same whatever. And it's like, no, space weather, it's very much like terrestrial weather. There are different susceptibilities depending upon what time of day you're at when something bad happens and what latitude you're at. So both latitude and longitude make a huge difference. Okay, so know that just in that lies an inherent redundancy in that sense, that not all of us are going to be affected the same way at the same time. Okay, and just that gives us a chance to ride out the storm, so to speak, even a bad storm, in a much better way than a lot of people advertise, just because they want to get more followers on YouTube. I don't know if you've noticed, but I don't do that. I really, it's not, to me, this isn't a popularity contest. I'm just trying to get people to actually learn what space weather is and what it isn't, so that we can adopt it more readily, and we can, we can make it our own, right? We can own it, just like we own terrestrial weather. Yeah, hurricanes happen, they suck. But you're not going to live your every day of your life in fear of a hurricane, right? You're just going to deal with it when it happens, and you're going to hopefully prepare yourself for if, it happens. I want the same thing for space weather. We really need to get to that point, and I'm not sure how to get there other than just doing what I'm doing. So I will continue to do so. So you guys can pelt me with olives all you want, or give me flowers for doing it, whatever. But this is the best way, I think, is to just kind of live and breathe space weather and not be scared of it, not be scared of it. Embrace it for what it is, and thankfully know what it isn't as well. Hopefully that addresses that point. 89, that's a bad flashback. Yeah, I know a couple of people who lived through that we were in like Toronto at the time, and it was bad. Both the East Coast of the United States and Canada had a horrible time. Since space weather will affect aviation in the future, what are the proposals for the aviation industry? Oh God, we're working on it. That's one of the things, for instance, I'm going to be giving a talk at the end of September to the FAA. There's some issues. Adoption of ADS-B, for example, is happening way too fast. And as long as we don't take away our secondary systems, our ground radar systems, we'll be okay. But if we rely solely on space-based GPS, navigation and positioning, and keep shrinking our traffic lanes, both vertically, horizontally, and in time, and make our planes sit that much closer to one another, we're removing all our margin of error, and that's not necessarily a savvy thing if we have a big solar flare burst like we had back in December of 2006. That would not be good. The radio burst can take out GPS for a while. And GPS reception, not the satellites. It just screams, the sun just screams so loudly that nobody on the ground or in planes can hear the GPS signals coming from the satellites. The signals are happening, I always call it the cricket in the train tracks, right? You can hear the cricket. If the cricket is near a train tracks, you can hear the cricket as long as there's no train going by. But as soon as a train goes by, is a cricket chirping? Maybe, maybe not. You don't know until the train goes away and it's quiet again, and then you can tell the cricket's chirping. The cricket was chirping the whole time, but you couldn't hear it because the train was so loud. Same thing with solar radio bursts, exactly the same kind of thing. And when the sun decides to be that train and it decides to chirp in the same frequency range as GPS signals or satellite phone signals, for example, then nobody gets it. Nobody can hear it on the day side, and that's an issue. So we've got to figure out how to deal with that. Oh, good. Thank you, Adrian. Pretty understandable so far. You bet. Absolutely. Lots of things overlapping, interconnected between the mini courses, so that's nice. Yeah, I always do that. I know it makes the courses a little bit longer, but because I only do them once a month, I always feel that it's important to kind of give a review. And then it's also nice that people who watch them back to back, they ingest all this information all at once, and then the next course they get a nice little review that maybe kind of reinforces what they already knew, or maybe answers some lingering questions that they had. So I'm glad you like that. I know it does make the courses a little bit longer. But okay, well, great to know we won't be without electronics, although some things might be fried, right? Yes, some things could be fried. Big things get fried. You know, if you had you can say, oh, will my pacemaker be fried? And it's like, well, if your pacemaker's the size of Lake Michigan, sure. But seriously doubt that. But will will grids have problems? Yeah, absolutely. As a matter of fact, anytime we have a G2 level storm or higher, they put in mitigating procedures to maintain reactive power, to do all sorts of things to take the load off the transformers, because the transformers, we don't want them to get hot, especially the old ones, because the old ones can become bombs very fast because they have other issues. They're wet transformers, and that's a very bad thing. You know, during a huge solar storm, I mean, you know, anything like you get with rolling blackouts, you know, brownouts, things like this, I would love to see the day where we have terrestrial, you know, weather broadcasters on the news saying, okay, we're bracing for this massive solar storm, and we're anticipating that we're going to be seeing some GIC, some ground current issues, which could affect the power grid. So anybody who can, you know, if you can turn off that extra light, if you can not have your hairdryer running, you know, if you can not do the laundry for the next, you know, couple hours or something, you know, just have things where people voluntarily try to take the load off the power grids in certain, you know, municipalities and in certain areas where people can kind of just dial back their usage and allow that grid to have a little extra breathing room. Sometimes that may be all we need. And just imagine if we could have news broadcasters just getting the word out to the general public that, hey, this is happening, and so, you know, don't worry about it, but let's just kind of make it easier on our utility companies for a short period, right? It's not a long, you know, maybe just a couple hours, maybe, you know, 5 hours or so, but it won't be like a week. It won't be something like that. And that may be just enough, you know, to help things out. Now, of course, power companies may come after me and say, no, don't do that. We won't make as much money. Well, what do you want, guys? I mean, you know, you want us to help you or not? So I don't know how all that's going to be embraced by you know, the political climate. But I do believe that the public is not, I don't think we are helpless. I think we absolutely can empower ourselves to ride even some of the strongest storms. But we have to be savvy about it, right? And one way to be savvy is to prepare. And one way to prepare is to have awareness, and that is where the newscasters come in. So that's part of the reason why I'm helping build trying to create the field of space weather broadcasting, so that we can ride out these storms in relative comfort and not do anything that you know, catastrophic to ourselves that doesn't need to happen. So hopefully that answers that. Okay, I'd like to see more underground power stations. Well, we'll see. That may be worse because it's really it's the ground currents. It's the conductivity of the ground itself that then induces currents into the power systems. If there is conductivity, if there's actually a potential difference in the rock, in the bedrock, and because of that, a current wants to flow, and if it looks at the power grid that's attached to it, you know, affixed to the ground, and it says, oh, this is an easier path, this is a less resistive path, I'll just use the power grid lines. You know, then that's what happens. That's how you get these ground-induced currents into the power systems, is that the electricity can conduct better through the power grid than it can through the bedrock. And that causes the issues. So having power systems underground may actually make it worse, not better. So careful what you wish for. You know, again, not my total expertise. I'd need to have a metal-telluric understanding, a better understanding, but that is my naive understanding of how it works. How do you think the sun will behave during the grand solar minimum in 2020 through 2040, like it is now? I think this next solar cycle, well, there are a couple of people who think that this next solar cycle is actually going to be a big cycle. I'm not sure about that. I think it's probably going to be similar to what we've had. But remember what I said earlier, similar to what we have means Carrington-class events are possible. And like I said, we saw nearly 3 of them this last solar cycle. So don't be super excited about a grand solar minimum, because you may get less activity, sure, but then you may get the really extreme events. It's just hard to say. Okay. Doc for president. Oh, you're cute. Thank you so much. Very kind. No, thank you. Not political. No. Okay. Yes, the radio bands will become active as cycle 25 picks up. Yes, yes, yes. Vote for Doc. You're cute. Okay, so let me jump into this. I've only got a couple charts left. We are now at the 2-hour mark. It's not the worst I've done, but yeah, I can tell my voice is going. So let me take a little sip of water, and then we'll get to the last little bit, which is kind of fun, only from the point of view of you get to see how insanely effective these fast wind streams are. It's unbelievable, but they really are effective when it comes to causing solar storms. And we call them solar storms. I wish we had a better non-vernacular, non-science jargon name for them. But we call them solar storms just like we call them the big CMEs, the big coronal mass ejections, that, the eruptions off of the sun. We call them solar storms too. I wish we would separate them more, but we don't always. Okay. So we talk about sources of major geomagnetic storms at Earth. Now remember, a geomagnetic storm, even though I've not really talked about it all that much, a geomagnetic storm is what the Earth's response is to a solar storm. Okay, so you have a solar storm that comes off of the sun, whether it be a big CME or just some fast solar wind, and yes, stream interaction region. That solar storm hits Earth, and the Earth responds by having a geomagnetic storm. If everything, if all the T's are crossed and the I's are dotted, then that's what happens. Okay, so now we're talking about geomagnetic storms. So this is Earth's response. Okay, so what's interesting, and we see, I'll try to stand over the text so I don't block the diagram. So you can see this little pie chart trying to show you really what is the percentage of different types of storms that happen at Earth. Okay, and of course, obviously, the big blue part of it, that is the big solar eruption, right? The big transient. This is what you would expect of big solar storms erupting on the sun, sending junk. The sun is belching all this junk toward us, and it hits Earth, and it causes the majority of big solar storms, or big geomagnetic storms, right? The solar storm causes a geomagnetic storm. Now, and I believe when they said single, let's see, a single CME, and then a multiple, what they mean multiple type, they just means complex things, meaning CMEs that when you have, oftentimes when the sun has a bad act or has a big sunspot, an angry sunspot, a bad active region, it fires off stuff in a series. It's just bam, it fires a solar storm and then a radiation storm, and then it fires a solar flare and another storm and another radiation storm, and it's just back to back to back to back to back. It just constantly, it's just angry. No matter what it does, it's just angry. It can't get happy. And so it just fires off storms the entire time you see it. So oftentimes in those cases, you end up getting multiple CMEs, multiple eruptions, and they will crash into one another. We used to call them cannibalizing until that became a bad thing to say, because it made you think something that wasn't happening. But you get these things merging and smashing into one another and compressing one another, and sometimes making it worse. So in this case, they actually tried to separate out the single type, which is the blue, which is the very pristine single, one big solar eruption, from the multiple CME, the more complex ones, which are the red. Okay, but all things considered, whether it's blue or it's red, over 3/4 of the structures that cause, the kinds of solar storms that cause a big geomagnetic response at Earth are from coronal mass ejections. But not all. There's a significant portion, 13% of them are caused by fast solar wind, stream interaction regions, which is pretty amazing considering we're only talking about major geomagnetic storms. We're not talking about the small ones. We're talking about the big ones. And it's like, oh my gosh, this is a significant fraction. So you have to realize that, we can't exclude them. And all this stuff is, if you recall, again, This is just solar wind. This is just the variability of the solar wind. It isn't even an eruption, okay? So that should set you up automatically to think, okay, well, what part of the solar cycle might actually be conducive for this kind of thing, where we're having fast wind, slow wind, fast wind, slow wind, and you see that kind of stream structure, back and forth and back and forth, because every time you get that interaction, you get one of these SIRs, one of these stream interaction regions that then causes potentially a major geomagnetic storm. Turns out there is a phase of the solar cycle in which that happens, and that's the declining phase of the solar cycle. And you can start seeing that here. So this plot here is showing a timeline from 1965 to 2010, a little bit past, no, 2010. And you're getting here, up here is the sunspot number, okay, and you see the cycles, cycle 20, 21, 22, 23, we haven't gone it. We are coming out of cycle 24, so you can tell this is an old plot. And then you have, on these three panels, you get large and major storms, okay, and this is the incidence of them over this time period. Medium and, medium geomagnetic storms, and then small storms, okay? Now, what the black and red lines are, the black line is due to coronal mass ejections, so the big eruptions from the sun, okay? And you can see large and major storms, you have a huge amount, a much larger amount of, of black, from the black line, it's much higher. You get a much larger amount of CMEs causing large and major storms. Then you get in the red are the little co-rotating streams, the stream interaction regions, okay? Which is what you'd expect. But when you get down to medium storms, they're almost equal. Now they happen at different times, but they're almost equal. And then if you get to small storms, oh my goodness, co-rotating streams actually cause the majority. So the interesting thing is that if you notice, look when, if I can get my hand in the right place, look when it peaks. See this right here? Both for medium storms and small storms. Look where it peaks. Where is it peaking? If I can get my hand straight, God, look, again, here goes the drunken sailor, look at me. Ridiculous. Notice that? That's not quite solar minimum, is it? It's kind of like the declining phase of the solar cycle, notice that? And you see that peak all the way down, even in the major storms, you see that where the little red peak is. If I can get my hand, again, in the right place here. See that little peak? Right? It's all at the declining phase of the cycle. Right? And again, the next cycle. See the next big peak? Right here? If you go straight up. Oh, that's not straight up. I should look at my hand instead of looking at this stupid thing. Notice, again, we're sitting at the declining phase of the solar cycle. And if you look again, same thing. If you look again, same thing. Every time you see a peak in the red from co-rotating streams, whether it's small storms, medium storms, or even the large storms, it always seems to happen at the declining phase of the solar cycle. Interesting, isn't it? Of course, the black stuff, that's the coronal mass ejections, well, that could be any time. The big ones, of course, typically peak during solar max, typically, but they can be anywhere. Really, it's just kind of a jumble. But the stream stuff always seems to peak at the declining phase. Now, why is that? I'll talk about that in a sec. I'll show you a really neat example. Before I do that, I'll show you this. This is from that same, this is Richardson and Kane back in 2012. They did a, excuse me, my voice is going so. They did a nice another set of pie charts, solar minimum storms and solar maximum storms, okay? They did a huge, Ian is so great about this. Ian Richardson, he's, the guy is indefatigable because he will go and dig through thousands. Do you see this? It says 1,128 storms. The guy will dig through a massive amount of data. That's 1128, and that's 991. I mean, how many years do you have to do to find this many storms? He and Hillary were just amazing when they did this work. So they did all these different storms for both solar minimum and solar maximum. And if you notice, at solar maximum, now we're not talking about declining phase yet, but we're talking solar maximum. look at this. For small storms, stream interactions were nearly half of them, right? That's the light gray. Coronal mass ejections for medium, large, and major storms. I mean, of course, major storms is basically the whole thing. But even at large storms for solar maximum, you had some stream structure that caused some large storms, right? But almost half of the storms at solar maximum were caused by stream, which is that light gray stuff, as opposed to CMEs. How about solar minimum? Look at this. Look at the stream. Look, it's 3/4 of the small storms during solar minimum. The solar minimum in this case included the declining phase, okay? And look, medium storms, still almost 3/4. Large storms, nearly half of them. And then major storms, it wasn't all CME driven, even the major storms, okay? So it tells you something that as you get close to that solar minimum period, that stream structures really contribute a huge amount, okay? And this is why. This is a picture that I just absolutely adore. Mike Cook put this together back in 2019, I believe. Do I have the year? Oh, I can't read the year. I think it was 2019. Maybe it was 2018. Oh, I can't remember. I'm sorry, my years are running together. This was during the declining phase of the solar cycle, and it probably was 2018. Because I think last year was pretty quiet. We got to, because this solar minimum is kind of dragging out a little bit. At least it feels that way to me. I don't know about anybody else. But here is the reason. If you take a look at the sun, now remember, we're looking at the bronze sun, okay? So we can see coronal holes. Again, it's not a hole, right? Let me stand over on this side so you can actually see me. It's not a hole. It just looks like a hole in this wavelength, okay? But look at this big boot-like structure. It almost looks like Italy, if I can draw it correctly, right? Okay, that boot-like structure, that is a coronal hole. It's a narrow coronal hole, granted, but it comes all the way down into the equatorial region, right? If I had to draw the equator of the, I don't know what strait is anymore. If I had to draw the equator of the sun, it's like this, right? So this is the ecliptic plane where Earth is, essentially. And so as the sun is rotating, okay, as it rotates, that boot-like structure, that coronal hole, is going to rotate past us. So we're going to see slow solar wind, and then we're going to hit that boot, that coronal hole boot, fast solar wind there, and then slow solar wind again, right? There's that stream interaction that we're talking about, right? Fast wind, or slow, fast, slow, right? And sure enough, back in August, the 12th of August, that's what the sun looked like. And we got, this was our KP. So we didn't quite have a storm, but we got active conditions. This is when this coronal hole was just beginning to form. It was beginning to really drop down. The very next month, 27 days later, this is what the sun looked like. See the boot? Now, granted, there's an active region growing in the middle of it. Do you see this cute little, blossom, right? That little bright thing. We actually did get a coronal mass ejection, and this happens very often during the declining phase. We get coronal mass ejections launched in and around these regions. Some of them, believe it or not, are stealth CMEs. So we actually had a CME embedded in this structure. And I don't go into the details, but that happens a lot. And it's just part of the game, which makes our job a lot harder when we look at solar wind data, because if there's a stream interaction region and a coronal mass ejection in there, it's really painful. But it can make for very strong storms. And sure enough, take a look at the KP. Now we see not just a minor storm at KP of 5, we get a KP of 6. And it lasts over a day, almost 2 days. Okay, we got a G2 level storm out of this. Okay, and then guess what? Here we go again next month. Now it's October. And what do we see? We see the boot again, right? It's a little bit better formed even. Now this time the active region went away, but the boot's still there. Okay, and what do we get at Earth? Once again, yet another storm. This time only a minor storm, but it actually lasts for about 2 days with the active conditions around it. Okay. And then the next month, it's still there. It's evolving a little bit, but it's still there. And what do we get? We get a G2 level storm once again, okay? Because we get a KP of 6. And then November 28th, so twice now in November, what do we see? Again, how many times, how many solar rotations is this? 1, 2, 3, 4, 5, 6. Oh my goodness, we're at 5, we're almost about to go to 6. This time we only got a little bit of activity, I think things were finally beginning to die a little bit. And then we saw it one more time before this hole finally collapsed. And once again, so it's back to December now, once again we get a G1 level storm from this thing. So there are 6 solar rotations every 27 days. Wham, wham, wham. Imagine pushing a swing, right? And if you push the swing goes higher, right? If you push it at the right time, it goes higher. Well, imagine the swing is like the Earth's radiation belts. and these coronal holes are pushing that swing, and it's pushing that swing right at the right time. One storm happens, the radiation belts get crazy. Oh, and they just begin to bleed off the charge, and then, oh, they get hit again. And it builds it up even more, and then they just begin to bleed off the charge, and oh, they get hit again. And it just keeps building relentlessly on and on and on. Satellite operators, especially in geo orbit, hate this time in the solar cycle because the radiation belts just do not calm down. They stay, especially the outer zone, what we call the outer zone, that's the outer belt. Anyone who knows the geo orbit skirts the outer edge of the outer. And that radiation belt is where all the, not all, but a lot of the electrons are. And because of the Earth's magnetic field is shaped very much, it's a dipole field, and so it's shaped very much like this in around the radiation belt. So if Earth would be sitting in here. So if this is the Earth sitting right here, okay? And the magnetic field very much in that area looks like a tokamak. And anybody who knows what a tokamak is, that's a particle accelerator. It goes round and round and round and round and round. And so you energize Earth's magnetic shield, and it causes those, it accelerates those particles. And they go faster and faster and faster and faster. And at one point we called them killer electrons. Now, again, just like cannibalizing CMEs, some of the scientists stopped really liking that because it became a misnomer to some degree. But these electrons from the declining phase, during the declining phase when we get these coronal holes and these fast wind streams, these particles would get so energized, so relativistic. The fluxes of 2 MeV electrons and greater, the fluxes would get so high that it would be, people would look at their spacecraft and they'd say it was like somebody put a crowbar between battery terminals. It just fried the entire spacecraft. You can get particles that really penetrate deep, deep down into the spacecraft electronics, and they just can't dissipate because it's not on the surface. It doesn't dissipate very fast. There's no sun to help do the photoelectric effect, the photoionization. So you can't get any, you don't get a bleed off of charge very fast. And depending upon the spacecraft materials, some materials don't bleed off charge at all, things like Teflon and FEP. They just don't. And so you just keep building this charge and depositing charge and depositing charge and depositing charge. And over time, eventually, you reach material breakdown because there's so much charge being deposited inside the materials that they just can't hold together anymore. Chemically, they just, you get lightning bolts inside, you get EMPs, all this kind of stuff, and the spacecraft goes dead, or that particular part of it, that component dies, which can do all sorts of weird things. So this is why spacecraft operators, especially GEO, can't stand the declining phase of the solar cycle. They hate it worse than any other part, including solar maximum, strangely enough. Pretty funny, huh? And this is also times when you find things like the third radiation belt. Oh my goodness, I'm back. Am I back? Oh, my internet died. My router just lost it, so I don't know how much longer I'll have before things die again. So, oh my goodness. And it looks like right now I'm getting really bad connectivity, so I don't know how long it'll last. Anyway, guys, let me shut this door again. A big thank you to Jerry who called me, and as I was beginning to realize things were going to hell in a handbasket, I have no idea. I think it's my, we have 110-degree heat out here today, and it's the hottest day I think of the summer as of yet, and so that may be part of the issue. So we're stable for the moment. We'll see what happens. Anyway, I think I was talking about the third radiation belt, and luckily I'm literally close to being finished here. I've got like one more slide. I was beginning to talk about the third radiation belt and the slot region, and that during these solar storms that are caused by the fast solar wind, we oftentimes get these third rings. You know, we see them all the time. And as a matter of fact, I can show. Whoops, on this side, I can show you what movie that shows it, and we get them all the time, not just from fast solar wind, but we get them also from solar energetic particles events that come in. We also get them from coronal mass ejections. We get all sorts of dynamics that occur in the radiation belts. But this is why satellite operators really despise these fast wind streams, is that unlike a solar storm that's an eruption, it's a one-off, right? It happens, it's done, and it's a one-off. In this case, every 27 days, you just keep getting slammed, and so you get these really dynamic radiation belt structures all the time, and you just can't escape them. And I'll show you, here's an example. This movie that I'm playing is actually, oops, no, we stand on this side, right? This is essentially a bunch of years of SAMPEX data. Every day you see here is actually one full day. And what you're looking at is a cut through the radiation belts. And you can see the outer zone typically, and then the inner zone. So the outer radiation belt and the inner radiation belt. But notice, oftentimes there's more than just two of them, right? Sometimes you'll see stuff come in from the outside. That's like white. That's even worse than red. It comes in like this. That is solar energetic particle events that come in from the outside and then come into the inner zone. But you can see oftentimes it's just a bunch of red all the way through here. So this is the reason why satellite operators, because you can imagine satellites going in and out of this all the time, because this is like, remember, this is a big ring. If I pull that slinky back up, this is just one part of that slinky. The slinky would come out and form a cone like this. And I'll do that here in a second. But you can see how incredibly dynamic these radiation belts are. And when we got to 2003 and 2004, for example, we had some really big solar storms. But you can see that there's just a lot of particle flux all over the place. So the last thing you want is to have those particle fluxes to stay in the red all the time and not be able to die down. Now that it's stopped, I'll show you. So imagine this, probably have to make it like really big and go over this way and tilt this way. So imagine, you're looking at the cone of this thing. Imagine if it were stretched out like this, okay? That's what you're looking at. You're looking right down the barrel of the gun, so to speak, but this thing actually stretches all the way around, and that's just kind of a cut through it. And so that's what you're seeing, is that this is one lobe of this slinky that comes out around the Earth, and the Earth is this black thing right here, okay? This black kind of like circle, or half circle. Okay, so imagine that being a black circle all the way around, that's Earth. And so you have another lobe on the other side, okay? And as you can see from the top picture, that is this kind of like a slinky going around Earth, all the way around. I'd be up here with this radiation belt here. If I move over just a smidge. Okay, that's kind of what you're looking at, is something like that. Okay, and so you're looking through a cut through of one side, with Earth being in the middle, right here. So that's really all I wanted to show. I mean, like I said, I was super close to finishing the talk today when my internet went down. Thank you so much for staying with me. It looks like I may have lost the chat completely, so I don't know if anyone is still able to watch, or if this is a new thing, or if this part is even going to be attached to the end of the other stream. I hope it is, and I hope you guys are able to see me, but I think I am no longer able to see your chats. As a matter of fact, I'll see if I can reload and see if it'll upgrade. But right now it said it looks like the chat may be dead. Let me reload. we shall see. I'm not sure, guys, but are we still? Let's see. Make it really big, stretched out. Oh my gosh, it's actually working again. Okay. So I lost part of the chat, but I refreshed, so it's back. Okay, let's see. So if you guys have questions, I'm in chat. Looks good. Good. I'm so glad. I can't believe I was actually able to connect back to the same stream. This is the first time I've had to do that, so I am just thrilled that it actually came back. And yes, Jerry, thank you. I think, what did it say? I think the link held. Yes, it did hold. I see it here. And thank you so much, Jerry. Jerry is one of my VIPs from Patreon and a beloved friend of mine. He also helps moderate some of this stuff, especially when things go haywire like today. So thank you, Jerry. You kind of helped me keep the morale and not want to give up, because I was ready to just kind of fold up shop. And I said, you know what, let me just keep working and see if people will hang out, just in case I could get back. So I was able to. Okay. So yeah, single-handed production is too much fun. Yeah, you should see me. I'm glowing quite profusely now because it was a little scary there. I can't stand it when I lose connection with you guys. It was really awful. So so hopefully this will now, I mean, I know I didn't go into very specifics about particular events that are fast stream related. I need to go into my database of satellite failures and degradations and stuff like that, and find out what ones were correlated with specifically with fast solar wind streams. And I haven't done that. I just haven't had the chance. Otherwise, I would have had examples, specific examples to show you guys, like I normally do at the end of my of the solar, of all the phenomena. But I don't think there's been a lot of, at least in academia, there's not been a lot of work done that correlates specific satellite failures with fast stream events. There has been that in the applied field, and I have to dig for those papers because those aren't in the typical academic journals. They're in they're in weird proceedings of the Spacecraft Charging Technology Conference or something like that. So they're a little bit harder to find, but I will do that at some point. Okay, so yeah, I'm glad you stayed around too, Magic Flim. Thank you so much. Do you guys have any questions before everything dies again on me? See, I wish I could get my hands on you to connect with me. Okay. Thank you, that's cute. Cheeky, but cute. Okay, great presentation. Thank you so much. How should a newbie start learning about this? Oh, goodness. I hate to say it, there really aren't there aren't any textbooks or anything like that on space weather that is for the non-expert. Really, that's something that we're just beginning to create, because there really hasn't been that much visibility of space weather to the non-expert. So it's kind of hard. You have to kind of look for primers. Obviously, my mini courses, if you can sit through them, because I've done probably, I don't know, I have probably 15 of them now. And they're anywhere between 2 and 3 hours long, depending upon the discussion sections that we have afterwards. And so you can start there. I know some people who actually binge watch my mini courses. I don't advise that, but there have been people who have done that, and I bow to you if you can actually do that. But the nice thing about the mini courses is that they are essentially jargon-free. There's a little bit of jargon in them, but not very much, not compared to what you'd find in an academic course. So, question: what happened to the other stereo A and B? Well, A is still functioning. B, unfortunately, had when we had what we call the conjunction, the superior conjunction. This was when the spacecraft were going behind the sun of your Earth, and these are the spacecraft. They're going behind the sun, and at that time, because they're having to communicate back to Earth, right? Well, as they go behind the sun, their antennas have to point almost directly at the sun to communicate to Earth. You can't really do that. As you're crossing back behind the sun, it'll burn the feed horns. So they had to actually change the orientation of the spacecraft and point the antenna feed horns away from the sun so that they didn't get burned up. And in the maneuvers, when they did that, stereo A made it through the conjunction maneuvers just fine. Stereo B had a gyro failure, sadly, and it caused it to just go into I think right now it's in an uncontrolled spin. And we woke Stereo B up one time a couple years ago, I think now, and we were able to determine that all of its hydrazine was frozen, its gyro had failed, and that's about all we got. We were trying to warm up its hydrazine because its batteries were so low. We had all the other functions turned off, but we had to try to turn on the heaters to thaw the hydrazine so that we could actually, which is the propellant, so that we could actually get the thing, maybe, try to figure out how to stabilize it. And it didn't work. And so Stereo B went silent again. And I don't think we've been able to resurrect it since. And I don't really know at this point if anyone feels that there's much of a chance of resurrecting it, simply because with a gyro failure, it's really hard to stabilize the spacecraft. And obviously if you can't communicate to it. But I'm sure we'll continue to try, especially as the spacecraft gets really close to Earth. We have a better chance of communicating with it if any part of it is still alive at all. The problem is the solar panels probably aren't pointing toward the sun. Or if it's in an uncontrolled spin, then the solar panels aren't pointing at the sun for any decent length of time, and so it just can't charge its batteries enough to keep it alive. So we're sad, but that's Stereo B. But Stereo A is still okay. Oh, thanks, Glenn. That's sweet. QRZ is a good source. Yes, QRZ is definitely a good source for radio stuff. By understanding electromagnetic induction and interaction of moving charged particles and magnetic fields, I'm obviously catching the middle of a conversation here. I spent some time watching activity in different wavelengths and keep watching to see if I missed something and or to see if I was mistaken in what I saw. Got to be careful. Absolutely, this is why scientists look at the sun in so many different wavelengths, is because we can see something in one place, and we think we see something, but we try to confirm it in a different wavelength and it's not confirmed. Or we miss something completely, and we can only catch it by looking at it in a different wavelength. We also look at different, the different types of imagery as well. So we don't just look at EUV on-disk images. We look at coronagraphs, right? We'll look in the HI. We'll look at radio beacon data to see if there was a shock wave, a radio burst that came out with it to give us any indication if there was an eruption. We'll look at stereos coronagraphs, because then we get a limb view instead of a front side, Earth side view. We'll get a view that's in reasonable quadrature right now. So there's all sorts of different things that we do to look at the sun in different ways to try to verify that we are seeing something, or make sure that we're not missing something important, especially with all the stealth CMEs that have been launched during this solar minimum. That's a big issue. As a beginner, what order should I watch your videos in? Which one is session 1, 2, 3, etc.? I probably should start labeling them. I think I have, in the mini courses, I have them set up. As a matter of fact, I got to put a couple in there yet. A couple of them I have, I have it, the most recent one is first, and so the earliest one is the very last one. So watch them in reverse order. Do you think NASA multiplies the data? Oh, manipulates the data? No. Oh, good God, no. And I'll tell you why in a sec, Glenn. I want to catch this other one. Greetings, Dr. Scove. I am a fan for some time. I appreciate very much what you are doing and hope you continue to give us proper science. I hope to understand enough soon so I can ask good questions. Thank you, Anjo. That was very kind of you. I saw my name up there in row orange, so I want to make sure I caught it. Glenn, getting back to your statement, no, the issue that we have with data, the reason why it looks like it's manipulated is because we get data dropouts, right? Or you see some weird thing in the data that, what is that? That is an anomaly. A lot of our scientific data is it's being put together by imperfect people that are scientists that have data, they have spacecraft and instruments that are performing in a very hazardous environment, and they're degrading. The instruments are degrading, or the launch environment messed something up, or we have electronics that's louder than we expected it to be. So scientists are trying constantly to upgrade their software and make things better and process the images and all sorts of things that NASA doesn't give us enough time to do to make stuff perfect. And so oftentimes we just have to put the data up with all the warts and all. It's really, that's why we have things called level 1 data, level 2 data. It's one of the reasons why we were talking earlier with Kyoto indices right now. There's a station that has caused the entire Kyoto DST index to go awry, and we just have to deal with it. None of this data is nearly as good as what terrestrial weather forecasters have. And these spacecraft, once we put them up in orbits, you know, we can't touch them after that. They got to just deal with what they have. And so there are a lot of problems with the data. Oftentimes people are doing tests or they're running this, that, or the other, and so the sun becomes blurry, or you'll get a filter wheel, or you'll get this weird difference image that, you know, then looks like there's aliens and babies and, you know, like something out of a Stanley Kubrick film. Honestly, that is just scientists trying to make the data better, or trying to recalibrate the system because, you know, they got something out of spec all of a sudden. The instrument's running hot, or they got this noise. They had a galactic cosmic ray pass right through the detector, and now they've got this bloom that took out this row of pixels. I mean, this is the real world. It's a lot messier and not as romantic as, you know, aliens feeding off the sun and Big Brother trying to cover up, you know, by removing frames from coronagraphs in LASCO. But to be honest, the honest truth is that these spacecraft, a lot of these spacecraft are very old, and space is hostile depending upon the orbit that they're in. These spacecraft are dealing with really bad environments, and it's degrading the instruments literally every single day. So, you know, this is the best we can do. And I wish I had a more fun answer. But right now, we're still trying to learn how to build instruments that can survive up there for long periods of time, let alone send, you know, humans to another planet. I worry about astronauts just trying to colonize the moon. You know, they're going to be sitting there on the moon during a radiation storm, and even the mining tools that they use will become hot, literally radioactive, because if you have metal mining tools and you have a radiation storm hitting these tools, you'll get bremsstrahlung right out of those mining tools. So not just the astronauts will have to deal with it, but the machines that they use and the rovers that they're in and the habitats that they're in will become sources of radiation. It's a very hazardous place. So the spacecraft themselves oftentimes become hot, which is a danger to the instrumentation. Okay, there's all sorts of things, and that's just one angle of many that I could go into that I won't go. You know, I'm already belaboring, I think. Okay, let's see. Yeah, everybody play nice. Thank you, Jerry. I appreciate that. You know, I don't mind the cheeky comments, but keep them cheeky and keep them clean. Don't get gross. Come on. I'm a mom. I'm a mom of a 10-year-old. Okay, so you know, right? And I'm a scientist. So, you know, cheeky is cute, but you know, don't go nuts on me, please. Scientists trying to mutilate to their great advantage. No, there isn't. Oh God, wouldn't that be great? I would love for those conspiracy theories to be right. For there to be aliens, for there to be, you know, major monstrous earthquakes being fueled by fast wind from coronal holes. I would love that. Not only would our scientists in this field get Nobel Prizes, but we would get so much more funding, because my field struggles to stay alive compared to astrophysics, compared to astronomy. Space weather barely stays alive. And I don't think there's a single scientist out there who wouldn't love to have all of these wonderful conspiracy theories be true, because we would get so much more attention and so much more visibility. Right now, we struggle to keep the bills paid. I have scientists and colleagues of that are my friends who have been driven out of the field because there's not enough money. So, you know, you can say all that stuff that you want, but really, it doesn't hold water. Okay. Scientists would love to have some of these really great stories to tell. If nothing else, it would make their careers. So sadly, the people who end up telling these stories are people who are not scientists. And that tells you something, right? They're trying to make their careers, but the scientists are still glued to the truth. So just be careful what you watch and what you listen to. And make sure it makes sense with what reality tells you is the truth. Okay, let's see. I have enough broken things on the bench, can't imagine what scientists deal with in space objects. Yeah, one of my closest colleagues who works at the Aerospace Corporation, he says, you know, if space were easy, anybody'd do it. It's not easy. And, you know, Elon Musk makes it look easy, but you have no idea the amount of tech support he has behind him. For instance, just from my corporation alone, because he does, you know, national security space, Air Force payloads, and aerospace is for, you know, we help keep those space assets safe. So we have an entire program office that stands up SpaceX. Now, we don't get credit for that unless you're actually an insider. They know we do aerospace. Like if you go to SpaceX and you say you're from aerospace, they go, oh yeah, we know. Oh my gosh, my gosh. But you know, the average person doesn't know that. We also help NASA. We help NOAA. We help all these different agencies because we know a heck of a lot about keeping space assets safe. But you know, it's not easy doing this kind of thing. And the new civil space agencies that are just beginning to get into this, they're going to find out very, very quickly. Sadly, I think Starlink might be the first thing where we get taught a really big lesson. I think Elon's ready for it, though. I think his point for getting Starlink up there was more to have eminent domain on the frequency bands, not so much worrying about how many of his little beloved spacecraft constellation, how much of that is going to fall out of the sky when a big solar storm hits. But I'm afraid that's what's going to happen. He's going to have a lot of spacecraft that are going to move to orbits he wasn't ready for. And we'll have big internet outages. So we'll see. We'll see. We'll find out. It'll be fun. No, if nothing else, it's an adventure. Okay. There is no immediate danger or enough productive technology that can be built using the current solar knowledge, I guess. I hope with the current space race, your field will have more exposition. I think so. I think this next solar cycle and the fact that we're becoming spacefaring, the fact that we want to go to Mars, the fact that we've got Artemis on the books, and who knows if we'll get there, but you know, we're trying to work for it. And Elon is pushing so hard to go to Mars. I mean, that's his thing, right? That's his whole thing. So that and the civil world of space, that growing so rapidly and wanting to mine asteroids and all of that, I think that is really what's going to push us over into the next level. And it's no longer going to be Air Force, really. That's you know, the dominant player in space. It's going to be civil. It's going to be commercial, and they're going to need different types of data products than the Air Force has traditionally wanted, or the Space Force would have traditionally wanted. And I think that can only help us as a field, because really it is. Space weather really is the new weather, and it's really going to need to migrate into weather in order to get the attention that it really deserves. Okay. No, Dizzle, I'm not mad. Relax. I'm not mad at all. You know, don't be sorry, don't cry. Oh my goodness. Just keep it clean. That's all. I'm not mad. I can go to Mars since they... Can I go to Mars since they are terraforming? Oh gosh, no. I won't even go to Mars. Don't listen to Neil deGrasse Tyson. He doesn't know what he's talking about. That's a totally different subject, but yeah, I could talk about that for a long time. Can any solar events actually damage my ham radio equipment if I ground my antenna inputs? Typically not, but there have been times I know that people have gotten shocked, strangely enough, during solar storms. Not really sure I understand that directly, but I've seen it. I've seen enough anecdotal information to kind of make my eyebrows raise. Where I've seen it happen is like in very dusty areas like Perth, Australia. There was one or two people that actually told me that they had gotten shocked with their antennas. I do know that dust storms can cause issues too. So I don't know if that was just a coincidence or not. But typically, you don't get that type of problem with solar storms. What you get, though, you get just your bands don't work, and then you're climbing all over your radio tower trying to figure out why things aren't working, and you don't realize it's space weather, and it'll clear up on its own. You think it's your rig, and you know, I really do that. One of the reasons why I think amateur radio operators appreciate, and the maritime operators appreciate it, is because they don't, when they know that there's inclement space weather, they're not spending hours tearing up their own electronics, wasting time looking for the gremlin that actually isn't there. So that's really where these forecasts become actionable and useful to many people. Let's see. Hopefully Trump will release some of the secret alien tech in his second term. Wouldn't that be fun? I would love to know what that alien tech might be. Let's see. Conspiracy theory in the morning, cute vac. I have read that we are entering a solar minimum for the next 10 to 15 years. What can we expect from the sun, and how will it affect weather on Earth? the sun is it's probably going to be cycles just like what we have. At least one more cycle. I think this next cycle will likely be that way. There are some people who think that this cycle will be really big. I'm not sure about that. I think it'll probably be similar to what we have. But as far as affecting terrestrial weather on Earth, I don't know. I am not a climate scientist. And we had a little bit of a discussion of that earlier in this talk. So if you want to go back a bit, you can review it. But you know, there's other things about space weather other than just our solar activity that that affects Earth. And the space weather that doesn't come from our star, that actually our star shields us from, which are mainly cosmic rays, the cosmic rays affect Earth. And so when our sun is less active, maybe it's not giving as much activity, it's not generating as much stuff that would cause Earth to heat up. But because it's not shielding us from cosmic rays that then also affect Earth, that may be affecting our climate in various ways as well. So this is it's a hot area of research, but it's just beginning to be studied by mainstream scientists. It's been the realm of fringe scientists for quite some time, and I'm very happy to see that we're finally beginning to get a little bit more traction in mainstream science, both in meteorology, terrestrial meteorology, with the neutral people, you know, the neutral particle people, neutral atmosphere people, and also space weather people who are looking at the charged environment, and how we look at their coupling really is going to be key, I think, into solving that problem. Let's see. Would a huge CME act like an EMP event? Yes, huge CMEs do act like an EMP event. In fact, it's categorized as an EMP class 3 event, because there's 1, 2, and 3. 1 and 2 are more weapon grade. 3 is a slow-acting EMP that acts globally. Thank you, Anjo. And it happens much more at low latitudes than it does at high latitudes, just because the way the Earth's magnetic field is. So EMPs are a bigger issue. They're an issue at mid-latitudes, but at mid-latitudes we more worry about the ground-induced, the geomagnetically induced currents in the power grids. Low latitudes, you worry about the EMP component. But yeah, you can look it up. It's called an E3 component. So it was kind of smart to blast nukes in space. Oh, if you're talking about the starfish days, my goodness, that was a little bit before me. As a noob to all this, could someone clarify if or when Earth's magnetic poles flip? Will the Van Allen belts disappear for a short time? I think they will. I think they will. I need to do a class on that. UCLA has done some really cool modeling where they've taken the Earth's magnetic dynamo, because they do a lot of geomagnetic modeling, trying to understand how the Earth's magnetic field flips over time. And very much like the sun, the Earth's magnetic field is not just a dipole field, that's the dominant field. But then there's all these other, you know, octopole, quadrupole moments, all these other moments that come into play. And it's the same kind of thing where I was talking about where, you know, you have a bathtub of water, and as long as the bathtub is full, you can't see all the toys in the bottom of the bathtub. Only after you drain it do you start seeing those toys emerge. It's the same kind of idea that if that water is the dipole field, as you begin to drain out that water, or drain that component and make it small, then these other toys, these other components of Earth's magnetic field show up, just like they do on the sun. And so we could very well go to a multipolar sun, whether it's a quadrupole or an octopole, I don't know. I would think we would at least have 4 poles. So we won't have a north and a south. We'll have like a northeast and a southwest and a northwest, and you know, we'll have multiple poles, and each one of these poles will have, you know, its own aurora band that goes around. But when UCLA has done some of these magnetic pole flip models, and then they've extended the magnetic field into space, oh my Lord, it no longer looks like this pretty tokamak shape. It no longer looks like this. I mean, you know, right where I've got the behind me, I've got the radiation belt, you know, kind of, you know, tokamak thing. It no longer looks like this. It's like a twisted taffy that's just like, I mean, seriously. It's like, do you think a radiation belt could survive in this? I'm not sure. and okay, now I've done it. Oh, don't you hate it when slinkies get like that? I gotta fix that later. At any rate, the issue ends up being whether or not those radiation belts would survive, and if so, you know, what kind of near Earth, you know, weather would spacecraft that still have to do geosynchronous orbits and still have to do sun synchronous and polar and all the same orbits they've ever had to do, because the ground isn't changed. It's only the Earth's magnetic configuration that has changed. So now what kind of space weather are they? My batteries must be dying, guys. Let me... Call me in less than a minute? Oh, good, good.
Yeah.
Okay, so I should be back on now. I just changed. So thanks, Jerry. Appreciate it.
Bye.
Okay, bye. Okay, so a few technical glitches today. Anyway, Jerry said that it looks like my audio was off for maybe a minute or so. Yeah, so you see, guys, single-handed production is not easy. No, it isn't. No, especially when I've had all these technical issues today. But anyway, so what I was trying to say was that when the Earth's magnetic field changes as rapidly as it is, and we have these models that really are very, full of speculation, the problem that we have is that we don't have a lot of anchors as scientists to go on. So a lot of scientists won't, they won't even participate. They won't even try to start doing any real science research because there's just too much speculation. And I think that gap will close as we begin to understand more about how our field is changing, as we get closer and closer, and as we start getting funding starts going in that direction, because things like the Air Force and by that time the civil commercial industry will need to know what the magnetic field is doing for predominantly for space weather, to be able to understand what spacecraft that are still in geosynchronous orbits and still in sun synchronous or polar orbits, those orbits are going to stay the same, irrespective of what the Earth's magnetic field is going to look like. So we're going to still need those orbits, and we're still going to need those satellites to be, being able to live out their mission life and survive. So that's coming. It's just going to take a little while before we get there. Okay. So, no, I'm just having, your net didn't go out. It's just technical issues. Anyway, well, I've also, we've been on for 3 hours once again. So, I mean, despite I don't know, how long was I out? Like 10, 20 minutes trying to do the internet connection. But we've, overall, I think this has been like a 2.5-hour course at least, and then about half an hour discussion. So thanks again, guys. You always keep me on for this long, and it's just wonderful. My heart goes out to you for sticking through it all and hanging out with me. Would I go into space? A very famous person I respect, or that I respected, once said that he sings about space so he doesn't have to go there. And I kind of second that. I know too much about how hard it is to do it. And maybe I would have done that before I had my daughter, but I would rather do what I do to keep other people who plan to go out safer, rather than risk my own life, especially when I know my daughter needs me. So likely no, that I'll just continue singing about space so I don't have to go there. Hopefully that answers that question. Okay, so do I get a certificate for this? No, but you are getting the same information that the Millersville students are getting. So you get the info without having the receipts, the social receipts or whatever we call them. But that in itself allows you to, you know, be able to hopefully teach other people and get them excited about space weather. So, oh good, it was pretty good. It cleared some things up. Good, Jeff, I'm so happy. Okay. Okay, come on, Dizzle. You know, when other people begin to complain, then you know, you're going too far. Okay. Jeez. Anyway, thanks, Elle. I appreciate it, Jerry. You guys, some of you guys are you know, trying to keep his collar on. Oh, come on, guys! Don't fight in the chat. I don't want to see that. All right. Being a good teacher is special. Thank you. All right, guys. Any other questions? Let's see. Is there an international community of scientists that study space weather? Oh my gosh, there's so many. Yes, there are tons of them. I can't even begin to talk about how many there are. It depends upon what part of space weather. Like space weather is, you know, from sun to mud, basically, and so there are tons of different consortiums. Some of them are in parallel; they work together. Some of them compete with one another directly, and I would need to know what particular aspect of space weather that you're interested in to even know which one I could direct you to. And I don't even know what they all are. I know some of them. Some of them that you've seen, you know, one of them, for example, is ISSI. That was one that you can actually see directly in my forecast. You can actually see the ISSI team where we were working on stealth CMEs and problem geomagnetic storms. These were geomagnetic storms that were caused by CMEs you couldn't see. And that's a big issue, even for, not just for spacecraft, but also for human spaceflight. Okay. Thank you, Anjo. That was a sweet thing to say. Barb says, is there a way to pay my subscription annually instead of monthly? Oh, I take it you're a Patreon person. You know what? I mean, I have to set up something different, and I need to. I've got too many people that are complaining about Patreon. I'm going to switch to YouTube, or not switch, but I'm going to add YouTube as my you know, as a way to do it. I don't know if YouTube will have an ability to do that, to pay annually, but I appreciate that. When I get a chance, I will try to find other ways of setting things up. But it's just been so slow because I'm just so, you know, slammed with so many other things. I think things will lighten up after January because I'm teaching 2 courses this semester for Millersville, which is overwhelming. And things will be a little bit better because then I'll have those 2 courses written and it'll be easier. But thank you for that. That's very kind of you to ask. I'm glad I've subscribed. Oh, thank you, Awesomus Maximus. I like your name. I'm glad I subscribed to this channel. Okay, any other questions? Oh, Patreon does? Joel White, you're saying Patreon now supports annual subscriptions? Oh, I've got to see that. I'll look that up. I didn't know. I didn't recall that they had. So, okay, yes, one-time fee per year. I will check that out. Thank you so much, you guys. I didn't have a clue. It tells you how often I look at Patreon's updates. I'm too busy putting new content out to look at the site. Okay, moderators would solve the chat problems, Tamitha. You need several. Many thanks to Jerry for helping. Yes, Jerry's great. Usually I don't have people that cause problems. Usually everybody plays nice. So I'm glad you guys are just, you know, just block him if he gets to be too much of a pain. I'm just kind of jumping over his conversation now. All right, any other, will we tunnel the moon? Oh, I see. You know, Jeff, that's a really good question. And by tunneling the moon, I'm assuming you mean building tunnels or building, you know, digging holes in the moon to, if for nothing else, for habitats. I think we're going to have to do that. I think if we really want a long-term colonization effort there, we're going to have to do that. These habitats that we have up on the surface are just going to be they're going to expose us too much. They have water walls and things like that. I've seen these habitats, but that's just it's not feasible. You can't stick someone in a coffin for 4 days while a radiation storm is ongoing. You know, we already have movies that show people going nuts in space, and imagine standing in a coffin on the moon for 4 days because it's a radiation storm outside and you can't leave. Do you think that's going to drive somebody crazy? It'd be like one of those hyperbolic chambers, what do they call those chambers? Those sensory deprivation chambers. My gosh, try doing that on the moon. You think that's not going to drive somebody into psychosis? So I think we're going to be forced to drill underground. Even at Mars, we understand that we're going to have to make use of some of the natural fissures. There are these big fissures that go underground at Mars. We're probably going to have to use those for habitats. It's not going to be Matt Damon, where you're hiding behind your little potatoes during a radiation storm. It's not feasible. Great for Hollywood, bad for reality. So, that's going to be the reality of it. Okay, so yes, I think I am tired. I think you guys, it looks like I see people saying, yes, I have to go, it's been great, but I have to go. And yes, we've hit the 3-hour mark. So let's, as you can tell from my voice, let's call it a day, guys. A takeaway from this course is the FSW is like the sun cracking a whip and smacking our belts like a rock splashing water to make a wavefront. Very cute. Fast solar wind, yes. Yes, it is. It is very much like that. That's a great takeaway in a nutshell. Don't have any questions, just want to say what you're doing is great. Thank you, Destruction Warehouse. I love it. Cool name. Okay. No, not Matt Damon. Yeah, I know. It's funny, isn't it? Okay. Thank you, Big Ben. I appreciate that so much. And can we for sure say that we have a dangerous solar storm this year? No, I don't think so. Especially this year. We have to start seeing sunspots, erupt, emerging again. We're not really seeing a lot of that, and I think the ones that are going to emerge by the end of this year are still going to be reasonably small. Some of the biggest ones we get, actually, and the most crazy ones we get are during the declining phase. We can get them during the ascending phase as well, but I think we have to see sunspots really emerge first before we start getting the really dangerous ones. So I think we're going to be okay for a bit yet. Okay, all right, guys, I think that's it. Living on the moon, are you serious? Yeah, well, that's what people are going to try. Okay, guys, I think that's it, and I will say goodbye. Thanks again for a wonderful 3 hours and hanging in there with me. And I will see you all again next month. Okay, take care.